Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on Math Basic Course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on aside as we jump into section 5.5 in the Big Ideas Math Integrated Math 3 textbook on solving exponential and logarithmic equations. We've seen hints of what we need to do guiding into this so far in this chapter, or maybe things from even previous things from IM2 or IM1, at least with exponentials. I know logarithms are new, but now that we've learned to condense logarithms, that'll be important for us, and rewriting exponents as well, and a lot of other logarithmic properties being involved as well. Should be good. We probably have to use the calculator here and there. I know inequalities show up. I don't know to what extent in the problem set. We do have 70 some odd problems to do. So I'm going to go ahead and get started. Jump to the description section down below if you'd like to download a PDF of the material. I don't think we have to graph, but we'll see. If so, I'll have graph paper ready for you to download. And then we have timestamps for each individual problem and any of the playlist if you need to see properties of old. Now, if we are using properties of old, I will probably brisk through those in the problems, especially if they slow down through them in the lecture portion. I'll do what I can in the problems to be quicker in making sense that we understand what we did from previous. Without further ado, I'm going to go ahead and get started. We are going to solve exponential and logarithmic equations and inequalities. That's a straight up thing. And our vocab is exponential logarithmic equations. So not much to say on the what you will learn other than let's see how to learn this stuff as a whole. Now, exponential equations are equations in which the variable expressions occur as exponents. Again, variables in the exponent. We have to solve it in a certain way. The result below is useful for solving certain exponential equations. If you have matching bases, you can set the exponents equal to each other. If b to the x equals b to the y, then x equals y. So attempt to get those bases to match each other. They probably won't present themselves immediately that way, so we can do that. If 3 to the x equals 3 to the 5, the only way that that's going to work out is if x equals 5, right? That totally makes sense. So set the exponents equal to each other if you can match bases. That's the way we'll say it. So, okay, well, if they don't match to begin with, you look at solve each equation. I have 100 to the x power equals 1 over 10 to the x minus 3. Can I rewrite these with the same base? Sure. I can turn 100 into 10 squared and 1/10 into 10 to the negative first power. Now, with this comes a little bit of distribution of sorts. 2 multiplies with x, negative 1 multiplies with x minus 3, and now you have a true matching base of 10 to this power equals 10 to this power. Just 10 isolated, no parentheses, nothing, equals those, so we can set those equal to each other to solve. They do a little double check. It seems to work out over here. Next one's a little bit different. This one's not going to be so much of a base match here, and because I can't raise 2 to a power to get 7 and whatever, they don't have a matching base. So they go straight to some log properties here. And there's more than one way you can write these. And honestly, this is how I used to write them most of the time, and I probably still will if the book's doing that. I want to show you an alternative, and it's one that explains the change of base with the I showed this in the lecture in the last section, but it explains the change of base formula as well. How do we get log base 2 of 7 equals this? Well, remember, it is log of 7 over log of 2, or natural log of 7 over natural log of 2. But let's say you don't know how to get there, and let's talk about what they're doing step by step here, first and foremost. First and foremost, why are they doing log base 2 on both sides? Because this base is 2 right here, and log base 2 of 2 equals 1. Well, why is there an x there? Because this has an x in the exponent, and the exponent can pull out and multiply in front. So what they're actually doing here, let's do a recap of that. 2 to the x equals 7. If they log both sides with the base of 2, what happens is the x pulls out in front on this side. And now it's x times log base 2 of 2 equals log base 2 of 7. And log base 2 of 2 is 1, so you're just left with x equals log base 2 of 7. So that's what they're doing with that. That's how this just turns into x, okay? 2 to what power is 2 to the x power? X is that number, right? But now that I'm using other properties, there's that. Another way of doing that exact same thing, instead of writing base 2 specifically, you can just have any log generically, such as just log. So 2 to the x equals 7. If I just log both sides straight up, regardless of base, as long as these bases match right here, just common log base 10, the x still pulls out, and this is x times log of 2 equals log of 7. So if we divide both sides by log of 2, we get x equals log of 7 over log of 2. So this one is more so a way to remind you of what you need to write in the calculator. I prefer this appearance of an exact answer personally. I think most people do, but this is how we're going to calculate what we do, and this is a reason why it's done. But as long as the lecture portion is explaining that they're logging with the base that's matching right there, we're all good to go, I think, from here. I just want to get that reminder of what I showed in the lecture portion before and what we're doing here, because this has nothing to do with matching bases other than matching the log bases here. Kind of interesting how it shows up in this setup here. I thought it was going to be its own thing. Okay. An important application. I don't know what this has to do. I didn't expect this to show up. An important application of exponential equations is Newton's law of cooling. This law states, sorry, miss, I'm going to cover you. The math is more important. This law states for a cooling substance with an initial temperature T naught, the temperature T after T minutes, capital T and lowercase t minutes, can be modeled by that big formula. That's new to me. So we'll probably have to copy and paste this later, where T sub R is the surrounding temperature and R is the cooling rate of the substance. We're probably doing just substitution and then solving. Use Newton's law of cooling with T, capital T is 100, T naught is that, So we substitute some values, we do some simplification, and then they want you to solve for what time, lowercase t, how long will it take to cool this to here. So they're jumping you again straight into another thing where you have your variable in the exponent, only this time e is your base. So if you notice, they do some stuff here, they get some stuff worked out, they divide by 142 and round your number. I'm never a fan of early rounding, so I'm probably going to leave it as a fraction until then, or at least the exact number in my calculator. I'm sure they have at least that. But notice what they do from this stage to this stage. They naturally log both sides. They take the natural log of both sides here and here. Now, why do they do natural log? And I might sneeze here in a second. Why do they do natural log? Because this base is e. So if you do natural log of e to some power, again, natural log is log base e. Log base e of e is 1. Natural log of e is 1. So this exponent pulls out, multiplies in front of that 1, and you're just left with this. So they are fully intent, and I'll do it as well. They are fully intent on logging both sides with the base that matches the base that they have in this setup. Log base e is natural log. If you natural log both sides, that cancels. And here you have whatever the natural log of 0.211 is. Then you divide both sides by negative 0.46. This is the way that we solve exponential equations. This is why logarithms exist as a function. Your calculator is very aware of how to log, how to raise things to certain powers and get your numbers. And this is what we're going to do. So about 34 minutes before serving the stew, apparently. So I don't know if we have to use this exact formula. Obviously, I'm going to go back, copy and paste it. I don't know it. I don't remember. It's my first time ever seeing this. Notice it means no. Yeah, so I don't know. I don't have much to say on it. So if we have to use it again, I'll copy and paste. If we have other word problems of the set, we're going to be ready to solve. And that includes problems where we did the principal interest rate things, continuously compounded interest and all that stuff. They might not say how much money do you get over this time. They might ask how much time it takes to get that amount of money. And that's solved using logs as well. Solving logarithmic equations. Logarithmic equations are equations that involve logarithms of variables. You can use the next property to solve some of these. If given some condition of positive numbers, b doesn't equal 1, if you have log base b of x equal log base b of y, that's only possible if x equals y. So logs of matching base isolated on both sides of the equation means you can set these equal to each other. Now, an important caveat, and I'm sure they're going to mention it, I'm sure we're going to do problems with this. An important caveat is it needs to be a single log on both sides. One log here, one log there. You can't say if log base b of x plus log base b of y equals log base b of z, then x plus y equals z. That is not what happens here. In fact, we're going to probably see not the exact opposite. We're probably going to see an exact example of what you do in this scenario, which is you have to condense these. You have to condense these. We learned in our last section that the sum of two logs is equal to the log of a product. You got to multiply them. It's not x plus y equals z, it's x times y equals z. But you would write another step before that where you would bring the logs in as one. I know I'm writing beyond what they're probably going to do for you later, but this will work out that way. Now, the only other thing that we have to talk about when we're solving for these things is be careful with extraneous solutions. We might have some things that introduce quadratics, and with quadratics, we might solve for answers where x, if x is your variable, x is negative, or x is 0. Well, you can't take the logs of negatives or log of 0, so make sure you substitute back in there or take a look at what happens when you plug in those numbers and make sure that it introduces nothing extraneous. So let's see what they say here. The preceding property implies if you're given an equation, you can exponentiate each side. Okay, so all's good there. We're looking good. All right, let's see some examples of this. Solve. Natural log of 4x minus 7 equals natural log of x plus 5, and then log base 2 of 5x minus 17 equals 3. The first one is because they're matching bases in both these logs, are both log base e, you can set the insides equal to each other. Now, they're not showing this part here. They might have just been hinting at it before, but if I did e raised to these powers, you'd also be left with this as well. So that's just something to remind you of how certain properties work. I think moving this way is probably more beneficial now. And yeah, you solve for x, right? You get x equals 4. Now, again, you might want to double check. They're doing a double check. It's all working out. Next equation, they're also double checking. It's all working out. So what do they do on this one? They rewrite this. Okay, they're showing the exponent version here. If I raise these as powers with 2 as your base, you can get here. Now, you don't have to write this if you still know your conversion from logarithmic form to exponential form, where we just say 2 to the third power equals 5x minus 17. And that's exactly what they end up getting here. This is 2 to the third power. Here's 5x minus 17. So I'll probably work it more that way instead of doing their actual this right here, which exercises the property that these cancel out, this thing grounds, stuff like that. I'm not going to write it that way, but eventually you get x equals 5 from that scenario. They double check. It seems to work out. Because the domain, okay, now they're talking about it here. Because the domain of a logarithmic function generally does not include all real numbers, be sure to check for extraneous solutions. You can do this algebraically or graphically. So this covers two things in one, and I mentioned both on the previous page, which is, first of all, you do not solve a log equation as is until you've condensed into a single logarithm, number one. Number two, if some answers are introduced by the nature of turning in quadratic that wasn't before, you might get some negative answers or answers with 0, just something that turns into what would be extraneous. I can't plug in, as far as this equation goes from the jump, these x's have to be greater than 0 on this log, and x's have to be greater than 5 on this log. If I get any single answer for x that is 5 or less, it's going to be extraneous. It doesn't have to just be negative or 0. X equals 3 is going to be an issue. So what we're going to do here to solve, however, is we do have two different logs of the same base. We must condense them into one before we get rid of the logarithm in the problem, so condense them through multiplication. This is a product. The sum of two logs is the log of a product. You multiply them. So from there, remember, this is base 10. So 10 to the second power equals this guy here. 10 to the second power is 100. You can distribute here, and you can solve this quadratic. They subtract 100 over, they divide everything by 2, as I would do, and they factor. They get x equals 10, x equals negative 5 as their solutions. As you can tell, 10 should be fine, negative 5 will not be fine. It's extraneous because that introduces logs of negatives. You cannot take the log of a negative. Why does this come to be again? Because we turned something quadratic that wasn't before. We turned something into that product, and when separated, they weren't like that. So together, they may be okay. Separate, no. And that's the original equation, separate. So we can't have x equals negative 5 as a solution to the original equation, or at least prior to merging as a product. Solving exponential and logarithmic inequalities. Exponential inequalities are inequalities which variable occurs as the exponent, so b to the x is greater than b to the y, something like that. Logarithmic inequalities are inequalities where logarithms appear in your inequality set, so like that. So this is pretty straightforward with this. If this is greater than that, then x is greater than y. If this is less than that, b is less than y. That's as long as b is a positive number greater than 1. If it's 2, if it's 7, if it's 20. If b becomes, and I don't know if we're going to use negatives, but if it's a positive number between 0 and 1, like 1/2, remember, the more times you multiply 1/2, the smaller it gets. So if b is less than 1, and it doesn't look like they're bringing that up, maybe they won't, but if b is less than 1, between 0 and 1, then the inequality flip-flops. We'll see if they hit those. And this is true for logarithms as well. As long as your base is greater than 1, then that side needs to be greater than that side for your setup. We'll see what else we have to do in the inequality front. Let's see what examples they show. So, in these examples, 3 to the x power is less than 20. If we log both sides as they did before with base 3, then this inequality should stay facing the same way, just like an equation. X needs to be less than the log base 3 of 20. Remember, these parts cancel out. X comes out in front. I'm not going to keep describing that each time in the problem set if it's as simple as doing that each time. So that's what happens. Log base 3 of 3 to the x is just x. And we calculate this using log of 20 over log of 3. Excuse me. If they ask you to round, log x has to be less than about 2.727. A logarithmic inequality, log of x is less than or equal to 2. Remember, this is log base 10, so we can rewrite this. Ooh, this is where it's probably better to use the property that they're having, because if I did my whole rewrite in exponential form, I say 10 squared equals x. The problem is, which side does the inequality go on? Did I just invent which way it goes, or do I just say it goes this way or it goes this way? Which way does it go? So this is probably better to talk about this the way that they do, which is raising these as exponents with 10 as your base on both sides, so you know the inequality stays the same direction. So that is an important reason to bring that up this way. So 10 to this power equals 10 to that power, or is less than or equal to, and notice that the less than or equal to stays this direction. So 100 is on this side, and this part cancels to be x on that side. So I think by the time that we hit these problems, we're going to have to use this property as a for sure. X is less than or equal to 100. However, in this scenario here, it says log of x is only defined when x is greater than 0. Remember your domain. This needs to be a positive number. So it's not just less than or equal to 100, it also needs to stay above 0. So there's a good set for your domain. Okay, that's the end of the lecture portion. Let's go into the vocabulary and concept check, numbers 1 through 4. Then we'll hit the problem set, I believe is 5 through 74, something like that. All right, complete the sentence. The equation 3 to the x minus 1 equals 34 is an example of a blank equation. That's an exponential equation. Now, that's not new to you, but just exponential functions have the variable and the exponent. Number 2, writing. Compare the methods for solving exponential and logarithmic equations. Well, they are similar-esque. I don't know if similar-esque is a word. I say it all the time. Let's see if it is. Not really. They're similar-esque in that if you can, well, what I'm going to say is if you can get match bases on both sides, you can set both sides equal to each other. Now, there's something else that I really should say, which is that not everything is going to be about matching bases, right? We saw 2 to the x equals 7. What if we say log base 2 of x equals 7 or something like that? Or log base, 2 of x equals 7. If you have something where you can't match bases, what you have to do is use inverse properties. If I have exponents, an exponential equation, I might have to log both sides to solve it. If I have a logarithmic equation, I might have to raise both of those as exponents to both sides to do equations. So the thing that you're going to have to also keep in mind, I might have written that there, but also, again, if I have some sort of b to the x equals, c, I'm going to have to log both sides of this with base b in order to solve. X is log base b of c. And then if I have an equation with logarithms, like log base b of x equals c, I'm going to have to raise both sides. You can rewrite it in exponential form, but the idea is you can raise those both as exponents with that base of b, and suddenly you have x equals b to the c power. So there's also that as well. They have inverse properties in play in order to solve the other, because they are inverses of each other. Number 3, when do logarithmic equations have extraneous solutions? Well, for me, I'm going to start hunting for them when you turn something into like a quadratic that ordinarily wasn't. But when do they have extraneous solutions? Yeah, I'd say when condensing logarithms. When condensing logarithms, I think is when it's going to happen. Because there's more than just when you multiply to become quadratics. Something else can become extraneous when you have subtraction of logs, because then it becomes a division problem. And in that division problem, we can't divide by 0 either. So there are a lot of different things that can have extraneous solutions that present a new type of function, such as a quadratic or a rational function. Rational is when you're dividing by a variable. That's the next chapter. When you're dividing by a variable, when a denominator has a variable in it. So those are instances when they have extraneous solutions. Oh, I think I should be less specific than that. When you take the log of something that's not positive. When you take the log of a non-positive value. That's probably even better to state than that. I'm really bad at these initial ones because they're not really problems. You know, they're just kind of questions based on the lecture. Complete the sentence. Number 4. If b is a positive real number other than 1, then b to the x equals b to the y if and only if x equals y. So what we're saying there, and this works both ways. It's not just if this is true, then this is true. It's also if this is true, then this is true, right? You can go both directions of this. And that's actually what they did. They said if you have something equal to something else, you can raise them both to some power with the same base. And that's going to be the case there. All right, you can also see a preview of what things are to come. So let's go ahead and get started on those. Numbers 3 through 70 or 5 through 74 are the set we're going to get started with. So strap in. Let's go ahead and go on this. Numbers 5 through 16 solve the equation. They put you right in the deep end. Right now we have 2 to the 3x plus 5 equals 2 to the 1 minus x. Because these bases match, we can set the exponents equal to each other. This will be 3x plus 5 equals 1 minus x. Add x to both sides, subtract 5 from both sides, divide both sides by 4. X equals -1. So it's all about matching bases, and if they already match, then you're good to go to set them equal to each other. Number 6. E to the 2x, hold on, my pen got changed, equals e to the 3x minus 1. E's equal each other as bases. Set the exponents equal to each other. I'm going to subtract 2x from both sides and add 1 to both sides. You get x equals 1. One simpler step there. I always recommend that starting in IM1. I say, when in doubt, try and keep your variable terms positive. So that's where I'd go with that one. Number 7, 5 to the x minus 3 power equals 25 to the x minus 5 power. Well, these bases don't match. So what I want to do is match the bases. 25 is also 5 squared. So if I leave this as a 5, turn this one into 5 squared, now I can get these bases more matching. This is still a 5 squared base, though. I need to turn it into 5 to just a single power. 2 needs to distribute and multiply with the x and -5, and this becomes 5 to the 2x minus 10. Remember, it multiplies to both, not just the x. Now the bases match. Now we can set the exponents equal to each other and continue solving. I will subtract x from both sides and add 10 to both sides. I get x equals 7. I'm not double checking these, so I'm only hope I'm doing the basic algebra correctly at the end of this. So apologies if I'm not. I should be fine. Number 8. 6 to the 2x minus 6 equals 36 to the 3x minus 5. I'm sensing a pattern here that whatever we're doing with the odd problem, we also kind of do with the even problem. So in this case, one of the bases has to match. In this case, by squaring it, 36 is 6 squared. You just saw last time, right here, that we must distribute this 2 into both numbers here. To truly match the bases, 6 to this power, 6 to that power. 2 times 3x is 6x, 2 times -5 is -10. So we're going to set 2x minus 6 equal to 6x minus 10 now that the bases match. Subtract 2x from both sides, add 10 to both sides. We get 4x equals 4, and x equals 1. I'm going to double check one of these just to be sure. 2 times 1 minus 6 is -4. 3 times 1 minus 5 is -2. And 6 to the -4th power is 1 over 1296. And 36 squared, 1 over 36 squared is 1 over 1296. All right. Not doing that again. I didn't expect something so strange. All right, this time we can't really do a matching of base. So we're going to be thrown into the log realm, and I'm going to give some space on here. 3 to the x power equals 7. It's at this time that you'd like to log both sides with the base of 3. Log base 3 of 3 to the x power is indeed x. 3 to what power is 3 to the x? X is that number. And this is log base 3 of 7. Now in my calculator, guys, I'm going to put log of 7 over log of 3. I want to remind you that the official answer that we can put is log base 3 of 7. This is fine. X equals this as a rounded value. And I don't know if we're expected to round these ones. I'm just kind of giving you the heads up here. It's probably worth doing it. I think the examples do it, so I'm going to type it out. So log of 7 over log of 3 is about 1.771. As a single alternative, in case you missed the lecture portion of this, you can also do this. Take the same problem and log both sides, but not specifically with 3. The main reason I'm bringing this up is because maybe you forget this formula and maybe you don't know how this property works. But we should know this property here. What if I log both sides straight up, regardless of base? Let's just say base 10, common log. The x will come outside of here and multiply by log of 3. And then to solve for x, we divide both sides by log of 3. So x equals log of 7 over log of 3. You still get there. I like this official answer more as an exact one than this one. This is what we used to calculate, though, that number. So there's a thing. Now, I'm not going to show that each time. I just wanted to make sure you're well aware of that. Number 10. 10 to the x equals 33. 10 to what power is 33? Well, figure it out. Again, always leave space on these if you want to hit the log in your work. I will log both sides. I can use any old log, but if I use log, the common log, this is really nice because that's log base 10. Log of 10 to the x power is just x. Now, I'll talk about that more. This is exactly log of 33, and then we can just use that for the answer, right? This is an exact answer, and I'll do log of 33 right now, and we'll kind of talk about that given the other property thing that I just used before. So it's 1.519. 10 to that power is going to be 33. That's rounded. Remember, what I previously did before is you spit the x out, you divide both sides by log of 10, but hey, the log of 10 is 1. So log of 33 over 1 is still log of 33, and that's all you get from that. All right, we are ditching logs for now on this stage. Not to say that you can't use logs on these ones, but at this point, you might not want to, as we're just trying to seek exact answers as they are. We're going to try and match bases again. These ones get a little bit different appearing, though, with regard to what the numbers are. We do want to see if we can match the same base here. Now, the lecture portion had the same kinds of bases, so we can use those. 100 is 10 to a power, so is 1 over 10. 100 is 10 to the second power. So if I raise that to the 5x plus 2. And 1 over 10 is 10 to the negative first power. Right? That's how those negative exponents work. They're actually fractions. Now we have to distribute these things, the 2 and the negative 1, into these. And now you have 10 to the 10x plus 4 equals 10 to the negative 11 plus x. I'm going to write x minus 11. I'd rather have that. So now we have matching bases. We can set these parts equal to each other. Listen, if you'd like to log both sides from here, you'd get to the same stage, right? That's how the property also serves its mathematical function. This isn't a magic step that if these two equal the same thing, you can log both sides. You'll still get here. Anyway, subtract x, subtract 4. Oh, hey-oh. X equals negative 15 ninths. Now, there's a reduced fraction. You divide both by 3, and that's negative 5 thirds. So that's a weird one, right? We ain't guessing and checking until we get that one correct. We're going to have to make sure that we do the extra work to get there. Okay, number 12. 512 to the 5x minus 1 equals 1/8 to the negative 4 minus x. As you just saw from the previous problem, it's probably something where you're going to have to change base and get something to match. Now, there's more than one base that you can match on these ones here, but you always want to go for the biggest base possible so you can avoid smaller numbers here on out. Just so you know, 8 is 2 to the third power. 512 is 2 to the ninth power. So you could do some form of matching 2s, but 512 is also 8 cubed. So we're going to have to, I'd prefer to work off of 8s if I can. So 8 cubed to the 5x minus 1 equals, and that's 8 to the negative first power, as you saw from the tens, to the negative 4 minus x. Distribute the 3. And distribute the negative 1. I'm going to put the x term first, positive x plus 4. Bases match and solve. And as expected, like its even counterpart, we're probably going to get a fraction answer here. Subtract x, add 3, divide by 14. 7 over 14 is 1/2, 0.5. Number 13. We have 5 times 7 to the 5x power equals 60. Now, in cases like these, first of all, I got to divide both sides by 5. And you get 7 to the 5x equals 12. Remember, 5 can't multiply by 7. 7's being raised to that power. I got to solve for x. I'm going to give myself some room here. I got to solve for x. I can't match these bases the way we'd want to, so we should use logarithms instead. Let's use log base 7 on both sides to ground the exponent and cancel out the 7s there. This will be left with 5x. 5x equals, log base 7 of 12. So as an exact answer, you can write something like x equals log base 7 of 12 all over 5, or 1/5 times log base 7 of 12. You could do this, and this will help show how you type this in the calculator. Log base 7 of 12, that's fine. If 1/5 times that works, then you could also write, because here's an exact. I'm good with that. Now, as far as the calculator goes, this is 1/5 times log of 12 over log of 7, which helps remind you that, well, the 5 multiplies with the 7 in the denominator. So in the calculator, I can do this, but in the calculator, you definitely have to put parentheses around the 5 in log of 7, right? So as far as order of operations go, so here I can type log of 12. And remember, you can use natural log for any of these things when you do the both sides kind of thing like this. Now, when I do 5 times log of 7, I cannot do this without parentheses if I'm going to write this all in one step. I can do that. This will be the correct answer. So 0.255 is the rounded value. Let's see some equivalents of this. I could have also done the straight up, because it was log base 7 of 12. I could have done natural log of 12 divided by natural log of 7. And then I could have divided that by 5. You can do it straight up like that. I know that looks trickier for you. This is why you might not know that you can do that, but I'm still going to get the same value out as a result of that. So there are a lot of different ways that you can write what it is that you're doing as long as you get there. What you don't want to do is you don't want to do the first one that I did here, but without parentheses, because this will just divide it by 5, and then it'll multiply the result by log of 7, the entire answer, not just that part. This is incorrect to write. Notice this will be a different answer, 0.122. That's not the correct answer. Not. Our correct answer is 0.255. We're doing that one, at least as far as rounding goes. I think we should be rounding. They didn't say that, but the lecture thing did. I want you to confirm what you're doing there is correct, especially when we hit some word problems. Number 14, more of the same. 3 to the 2x, or 3 times 2 to the 6x equals 99. We have to isolate the exponential term first before doing anything else. Otherwise, it's a little more work. There are other ways we can go about solving it from there, but I'd refrain. If I divide both sides by 3, you get 2 to the 6x equals 33. Now, in this case, 2 to some power doesn't equal 33 as far as matching base, so let's do log base 2 of both sides. Like that. So 6x will equal log base 2 of 33. Handwriting worsens as I go along. X equals log base 2 of 33 all over 6. So here's an exact. I'll just leave that as the exact. The approximation, I'll go back to the calculator and let's do log of 33 over log of 2 divided by 6. Like that. So the top part is log base 2 of 33. And then we're dividing by 6, and then we should get that result from there. So 0.841. Sure. Right? Sure. Okay. Number 15 and 16, you can see E as your base. So the best log that you can use in these cases to cancel things out will be the natural log. 3e to the 4x power plus 9 equals 15. First, get e to the 4x by itself before doing anything else. Subtract 9 from both sides. Divide both sides by 3. You're going to get e to the 4x equals 2. Now, as I'm separating those, that's because I'd like to natural log both sides. If I do that, that'll cancel out the e portion. It'll just leave me with 4x. So 4x equals natural log of 2. Boom. Divide by 4. X equals natural log of 2 all over 4. You can also put 1/4 times natural log of 2. Totally up to you on how you want to write that portion, as a fraction, as all divided by. I think we tend to use the other one more, natural log of 2 all over 4. I can even type 0.25 times that, which I'm typing in my calculator. 0.25 times natural log of 2, I'm getting 0.173. 0.173 as an approximation of that. Okay, let's go to number 16, last one in the block. Two e to the 2x minus 7 equals 5. More of the same. Get e to the 2x by itself, add 7 to both sides. Divide both sides by 2. This is where I'd like to natural log both sides. Now we have 2x equals natural log of 6. Divide both sides by 2, we get x equals natural log of 6 all over 2. Which, of course, is, I don't know. I know that, e squared is 7.4, so this is less than 2. Oh, you have to divide by 2. This answer is less than 1, but not much. Maybe in the 0.8, 0.9 range. Let's see. Natural log of 6 divided by 2. 0.8958. So 0.896. 0.896. That was kind of close. Between 0.8 and 0.9. Significantly closer to 0.9. All right, numbers 17 and 18, we have modeling with mathematics. The length L in centimeters of a scalloped hammerhead shark can be modeled by the following function. L equals 266 minus 219 e to the negative 0.05t. Normally in word problems, we do a lot of rounding stuff here, so it makes sense that we did some practice beforehand. T is the age in years of the shark. How old is a shark that is 175 centimeters long? L is already in centimeters, so we're going to do exactly that. A substitution of 175 for L, and we need to solve for T. T is in the exponent, therefore we're going to have to do some logging to solve for it. That's what logs do. So we have to get e to this power by itself first. We're going to subtract 266 from both sides. I don't want to make a mistake on this. Otherwise, everything goes awry. So I'm going to do that single subtraction. I get negative 91, plus I need to use this number later. Negative 91 equals negative 219 e to the negative 0.05t. We're now going to divide both sides by negative 219. Now, I doubt that these things not only are an exact good decimal, I also doubt that they reduce at all. Let's check on all that, and I need the number anyway. Now, negative divided by negative is a positive, undoubtedly a poor decimal, and also not a fraction that reduces. So I'm not going to write a rounded one. I'm going to rewrite it as 91 over 219, but positive. And this is e to the negative 0.05t. It is at this stage that you should log both sides. Not any kind of log, but natural, or not just any log, but natural log. Okay. So from here, you'll now have negative 0.05t on its own side of the equation. And over here, you have natural log of this value. Now, 0.05, this is going to be me being a little bit, like more iffy in particular, what have you. 0.05 as a decimal is also 1 over 20, right? Hold on, I have to double check that. It's 1 over 20 is indeed 0.05. So if I multiply both sides by negative 20, that's the same thing as dividing both sides by negative 0.05. I bring that up because I like to write exact answers before this that look good. So t equals negative 20 times natural log of 91 over 219. Now, before I compute the answer, I want to ask myself if what I'm doing can make sense as an answer to begin with, because that negative can throw me off and think, wait a minute, we're going to get negative years for this answer? Not exactly. You have to remember, log of a fraction less than 1, see, log of 1 is 0. Log of numbers greater than, regardless of base. Log of 1 is 0. Log of numbers greater than 1 are positive. Log of numbers between 0 and 1 are actually negative. E to a power that gets to a fraction, you're doing some 1 over e, that's going to get you a negative. So we're doing negative times negative to get positive. Now I'm going to use a calculator to get the rest of it. So we get negative 20 times the natural log, sorry, and I've got a head scratcher thing going right now, by the way, over 219. Now, is this the correct answer? I'm going to hope so. Can a shark live about 17.56 years? Sure. So what did it say? How old is a shark? So the shark is around 17, 18 years old. I'll say 17.6 years old. 17.6 years old. See, it was a positive answer as a result of everything that we did. And I'm just going to trust that their model that they gave us works out for whatever they're talking about, shark's length and its age. Very cool that they have that information provided for us and that we could get that. All right, number 18. Now that we've gotten an idea of what's going on, let's do more of the same. 100 grams of radium are stored in a container. Oh, that radium. The amount R in grams of radium present after T years can be modeled by this. It's basically radioactive decay. There are other problems that we do that talk about half-life stuff. This might be the equivalent of doing a half-life version of this. After how many years will only 5 grams of radium be present? It's going to be a lot of years, guys. It's going to be probably in the thousands. Thousands, tens of thousands. This is very little reduction here. So only 5 grams left. We started with 100. Now we have 5 left. So we're going to, of course, divide by 100. And 5 over 100 is 1/20th. We just saw that that number was 0.005, in case you're interested. We could write that as 0.05, I should say. 0.05. Let's write that exact one because it is still exact. So e to this value. Do I have the right number of zeros on this? I do. 1, 2, 3 zeros. Okay, this is where we natural log both sides. And of course, natural log of such a decimal will be negative. So I think we're on the right track of what we're doing. Negative 0.00043t equals natural log of 0.05. I don't know how to multiply this number by something clean, so I'm just going to straight up divide by this thing. Sometimes good looking answers can't be had the same way that you wish it could. So this is what I'm going to calculate. I'm going to divide both sides by that, and I'm going to calculate this. Natural log of 0.05 over negative 0.00043. And this has to be natural log. Now I want to bring something else up after this. How many years? Thousands. 6,966.8 years. 6,966.8 years. Okay. As an alternative, this is just me expanding properties to have fun with it. I did this in a previous one. Remember that this is also 5 over 100 is also 1/20th. Remember that we also natural log both sides. Well, I could rewrite the natural log of 1/20th also. Remember, that's a condensing thing, as natural log of 1 minus natural log of 20. And natural log of 1, log of 1 is 0, so that would become natural log of 20. So, or negative natural log of 20. So, if you're wondering here, what things are the same, what things are different, what have you, apparently the natural log of 0.005 should be the same thing as negative natural log of 20. I'm going to see if that works. Natural log of 0.05 and negative natural log of 20 in the calculator are both the same thing. Natural log of that, negative natural log of that. So you could have worked one way or the other on that portion. We could have found ways to clean up what we wrote instead of writing decimals. That's totally valid as well. So I'm just flexing some properties with you guys, making sure that you get a full understanding of where we're dancing around these numbers. All right, numbers 19 and 20 use Newton's law of cooling to solve the problem. So I need to go back and find that formula. 1 second. Okay, so now that I'm coming back, not only am I copying the formula, I'm copying the information because I don't know any of this stuff. I know T naught is going to be the initial temperature, but I need to bring everything else in with it. What T sub R is, what I know that I think I should know them, but I need to see it with the entirety of the problem. All right, so here we go. Let's take a look at this. So use Newton's law of cooling to solve the problem. You are driving on a hot day when your car overheats and stops running. Facts. The car overheats at 280 degrees Fahrenheit and can be driven again at 230 degrees Fahrenheit. When it's 80 degrees outside, the cooling rate of the car is R equals blank. How long do you have to wait until you can continue driving? So I know that R is this, and I know we need to solve for T. I need to figure out which ones represent what. Temperature T after T minutes. So we need, let's see, initial temperature T naught. TR is the surrounding temperature. So surrounding temperature must be the 80 degrees outside. Here's the surrounding temperature. I'll put degrees Fahrenheit. The initial temperature must be the car at 280 degrees. And then the temperature after T minutes. We need the final temperature, T, capital T, to be 230 degrees Fahrenheit. That's my guess on these things here. So let's do a substitution of that information. Let's say 230 equals 280 minus 80 times e to the negative r times t plus t sub r, which is 80. That's our information we have to solve for t. Let's hope that I set that up correctly. So subtract 80 from both sides here, we get 150. Take the difference of these ones, we get 200. It looks like good numbers because when I do division here, 150 over 200 reduces to 3/4, also 0.75. All right, 0.75. Was that an 8? It was. My handwriting's getting kind of bad there. I'm going to natural log both sides. Like that. So now we're getting negative 0.0058t equals natural log of 0.75. Or you can do something like natural log of 3 minus natural log of 4, because it's natural log of 3/4. You can have fun with that. If we divide both sides by negative 0.0058, again, I expect a positive answer here because natural log of this number will be negative, and we're dividing by a negative here. Do I expect the correct answer? We'll see. Let's see how long this takes. Time is in what? T is in... Doesn't say. Is T represented in the initial thing here? Oh, T minutes. So this is going to be in minutes here. So when we get this answer, let's see how long it's going to take. This is good information. I'm going to know this the next time that my car breaks down. I'm like, let's use Newton's law of cooling. All right, we're going to do natural log of 0.75 divided by negative 0.0058. We're getting 49.6. I'll trust that. 49.6 minutes, less than an hour. At least it's not something like, 60 days. I'm understanding the concept of the answer within the, all right, we need to cool it down a little bit. 80 degrees is pretty warm, but, 50 minutes will do. All right, let's go to number 20. You cook a turkey until the internal temperature reaches 180 degrees Fahrenheit. Let's see if I remember anything of this formula here. I'm going to try this out. Until it reaches this. I think I want that to be my final, right? So capital T, I believe, is that one. So 180 degrees Fahrenheit. The turkey is placed on a table until the internal temperature reaches this and can be carved. Oh, I'm sorry. This must be the initial. So this must be T naught, and then until it reaches this is the final, and can be carved. When the room temperature, that's T sub R, I believe, is 72 degrees Fahrenheit, the cooling rate of the turkey is R equals, man, there's a lot of information here. I guess I couldn't do this in my head because I don't know how cooling rates work. 0.067, how long do you have to wait until you can carve the turkey? So if I recall, the formula is, let's see, I believe it's capital T equals, and then we did our initial minus, oh, hold on. I'm just going to put the numbers in. So 100, I have to go back and check, equals 180 minus 72, difference of those ones, times e to the, was it RT? 0.067 times t plus t sub r. I know this one because I know we subtracted these and we subtracted those. I got to check the e to the RT part. Negative RT. Darn, I was so close. So negative RT. I would have caught that eventually when we would be dividing a log of a, when we'd be dividing a negative by a positive, I'd say, oh, that must have to be negative. Okay, anyway, very, very close. Okay, let's subtract some things. We get 28 equals 108 times this. I think it goes without saying that we're going to natural log both sides here. So natural log, no, excuse me, not yet. We have to divide by 108. So I guess it does. I guess we have to say some stuff. Divide by 108 first. Now 28 over 108, I don't think cleans up as a decimal, but it does clean up as a fraction. So its decimal sucks, to say the least. Its fraction can be written as 7 over 27. So let's divide both sides by 108. I'll go ahead and still show you the natural log step so you're not confused as to where we went here. So this is 7 over 27 here, and here is e to the negative 0.067t. We natural log both sides. Now I'm going to have some fun with the way that I write this stuff out this time. Hope that's okay. I'm going to rewrite this as natural log of 7 minus natural log of 27. Maybe that's a good way to remind you of why this should be a negative answer here, because you're subtracting something smaller by something bigger. Anyway, now you're dividing by, not a negative answer in whole, but just the negative log. Divide both sides by that. It almost seems like 0.067. If it was negative 0.06 repeating, that would be, I think, 2/30ths. but it's probably not exactly that, so I can't leave it exactly like that. So t, I'm going to calculate that. Let's go to the calculator for that one and figure it out. We're getting, you have to use parentheses around this though. Natural log of 7 minus natural log of 27. Was it 27? Yeah. 27 divided by negative 0.067. So 20.1 minutes. Okay. Cooling time for the turkey. About a 20-minute wait. I think I've heard of such things. Normally when I think of my steak, I'm thinking cool after 5 to 10 minutes. Turkey's a little bit bigger. Cooling rate of the turkey, a little bit different. I'm feeling it. All right, let's go to numbers 21 to 32 where we solve the equation. These are not exponential equations, but logarithmic equations. So we kind of do opposite of what was there before. Not opposite, but get the logs by themselves, match the basis of the logs, that kind of stuff, and then we can set the insides equal to each other. No extraneous solutions need to be checked until we start doing some condensing things, at least in my heart of hearts. I can do some basic substitution, make sure that they didn't set up a problem with the damaged answer. Like if x equals 1, it would be a problem because 4 minus 7 is negative 3. Can't take log of a negative. But you have matching bases right now, so I can set the insides equal to each other to solve. Subtract x, add 7, divide, we get 6. This is 24 minus 7, that's positive. 6 plus 11 is positive. All is good. Number 22, once again, matching bases. They're both log base e. So we can also, again, set the insides equal to each other. So we're going to say 2x minus 4 equals x plus 6, and do your best algebra. Subtract x, add 4. And positive, positive, all works out. It's very quick questions to begin with. Now, what they do in the book, just to remind you, or I don't know if they actually write this, but they will show this eventually. You can raise these as exponents with e as your base. E to the natural log of this is that. E to the natural log of this is that. So it does become that ultimately. Don't need to write it that way for now. I'm going to save those for the inequality problems when it seems best to do that. And you'll kind of see why when we do it. Number 3, 23, excuse me, number 3. That was a while ago. Log base 2 of 3x minus 4 equals log base 2 of 5. I definitely like parentheses around all these things here. All right, same base. Set these equal to each other. Now, I do want to keep stating, as I just showed in the last problem, the whole, and that should work, showing the whole base thing here. These problems aren't different from other problems that we did before. We just got to see more properties with it. If we said rewrite in exponential form, what are you used to in this scenario? Let's say it didn't say log base 2 of 5. Let's say it just said 5. And I said, okay, solve this one. Well, what you would do, and actually there are problems we're about to do with that on numbers 25 onward. You can see that. What you can do is rewrite in exponential form. 2 to the 5th power equals 3x minus 4, right? You would go to there. Well, this is no different than us in this problem. Now rewriting exponential form, say 2 to the log base 2 of 5 equals 3x minus 4. It's just 2 to the log base 2 of 5 is 5, right? So we still get there. It still gets there, or you can raise these both with 2 as the base. All that kind of stuff is involved. They're all interconnected. They're not different kinds of problems. You just have to use different properties in order to get there when it comes to solving. So it depends on how you want to treat them. So number 24 is a lot like the previous problem here. We have logs with base of 10. These are common logs. We can set the inside parts equal to each other. If you wanted to raise it with a certain base, 10 would be your base. But this is 7x plus 3 equals 38. Subtract 3 and divide by 7. You get x equals 5, and all positive results come from that one. Now we move on to ones that, frankly, I think we've been able to solve in the past if we truly wanted to. But now your exponent, now x is not the exponent. Now instead it is a number, and you're solving a different way. So log base 2 of 4x plus 8 equals 5. This is where we were doing what I just stated, I think, on 23. Rewrite in exponential form. This is 2 to the 5th power equals 4x plus 8. If you want to do it in that other form, raise them both with 2 as your base like that. 2 to the 5th equals, those cancel and you get 4x plus 8. Still works out. Anyway, this is 32. Subtract 8, divide by 4. And you get to 6. Let's see if that works you know, 6 times 4 is 24 plus 8 is 32. Log base 2 of 32 is 5. 2 to the 5th is 32, so that does work. All right, number 26. Log base 3 of 2x plus 1 equals 2. Rewrite this as 3 to the 2nd power equals 2x plus 1, or 9. Subtract 1 divided by 2. And all is well there. Hopefully the speed is okay, at least when we hit the algebra afterward. Number 27. Log base, because these can really work like clockwork in the way that if you do stuff like, I'm trying to do this in my head right now, I think I'm getting x equals 10 in my head. If you do enough stuff in your head, you can probably get to that answer. So I start with 7 squared, right? Equals 4x plus 9. 7 squared is 49. Subtract 9 divided by 4. Yes, x equals 10. So that's where, right? If you can do enough in your head, it'll work out. This one I probably don't want to do in my head, because 5 to the 4th is a bigger number, and that's what we're going to have happen on number 28. All right, to show you the different method, we'll do it in that different way. Raise these both as exponents with 5 as the base. 5 to the log base 5 of 5x plus 10 is 5x plus 10. 5 to the 4th is 625. So we're working it out in that stage. It's still the same result that you get to. 5 to the 4th equals like that. Subtract 10 and divide by 5. You get x equals 123. I think. All right, number 29 and 30. What are different on these ones? I guess x is on multiple sides. This is another one I don't know for sure. This is another one I'm going to just double check on my extraneous solution things. No, yet x is on the same side of the previous problems too. What's different from these problems and the first problems we had? Same base. Same base. We're going to set the internal parts equal to each other. 12x minus 9 equals 3x. Subtract 3x. Add 9 and divide by 9. You get x equals 1. 12 minus 9 is positive. 3 times 1 is positive. So that's all good. I don't know what makes these problems different from the ones to begin the set. I legit don't. I guess because these are logs instead of natural log. I don't know. I thought this was going to advance to something harder, if that makes sense. Number 30. I mean, if you have different bases, it gets a little wonky. We ain't playing that game right now. Okay. So set 5x plus 9 equal to 6x. Yeah, I'm kind of lost on how this is working. Subtract 5x, you get x equals 9. So positive, positive, all works out. That's the answer. We're all good to go. We're all good to go on those ones. All right, number 31. Now 31 and 32, they begin as quadratics. I don't know if, therefore, I have to double check my work because they began as quadratics. It's not like they turned into quadratics later. So that's an interesting part. Now, given this, let's rewrite it in exponential form. 2 squared is 4. And next time I'm going to write this on the other side. Subtract 4 from both sides. I get x squared minus x minus 10 equals 0. Not factorable. Well, we have quadratic formula to rely on for these ones here, and we might have to round our answers as a whole and just make sure that all is good. But here we are going to have x equals, I'm just going to go straight, instead of discriminant, I'll go straight into it. Negative b, which is 1, plus or minus the square root of b squared, minus 4ac, all divided by 2a. So that's 1 plus or minus 1 plus 40, all divided by 2. So these are the two different answers here, and I believe both answers for x are fine, meaning you can have the 1 minus root 41 over 2, because the bottom line is you're going to be squaring that x in the end, and everything's good as long as it's still inside the log, then it'll turn positive ultimately. Remember, it began as a quadratic, so it's not like it turned into a quadratic later. So I'm going to go to the calculator here. I'm going to type in these answers and see what we end up getting. What's interesting, though, is this began initially as something that was factorable, and then it became something that was non-factorable. So that's where we went with this one. We have 1 plus root 41 over 2. and then 1 minus root 41. Whoops, let's just repeat that answer. 1 minus root 41 over 2. So we're getting negative 3, or positive 3.017. Shoot, I can't say this out loud. 3.702 and negative 2.702. Those are approximate answers. So that was an interesting jump in problem. We never turned something into a quadratic in the meanwhile. I'm sure we're going to do some more problems with that, but there are the different kinds of answers that we have with that one. All right, let's do number 32, log base 3 of. So probably more of the same. It might be another quadratic formula kind of problem. Let's see. Log base 3 of x squared plus 9x plus 20. Well, that's not factorable, but let's see what happens when you do 3 squared. So 3 squared is 9, so this equals 3 squared, which is 9. Subtract 9 from both sides, and we get x squared plus 9x plus 18 equals 0. This one's factorable. This factors into x plus 6 times x plus 3. So you get x equals negative 6, x equals negative 3. Now, again, negative answers aren't a problem. The problem is taking the log of negative numbers, but you plug in negative 6 or negative 3 into here, you're going to get 9, right? That's the idea. So these aren't extraneous solutions. These were initially quadratic to begin with. It's not like it started as something that wasn't, right? So these began that way. So we're all good. We're all good. Those are fine. Excuse me. This one, in fact, here they're actually saying check for extraneous solutions on these. I didn't know this was popping up. So numbers 33 to 40, we got to solve and check for extraneous, and this is where they might appear because of the condensing of two logs, which introduces a brand new nature of the problems that weren't originally there. And that's how we have to solve these. We have to condense this log here into the log of a product with that base. Log base 2 of x times x minus 2 equals 3. So there's our initial setup for this here. Now I'm going to do 2 to the third power equals x times x minus 2. Like that. That's your work on that. Distribute. Subtract 8 from both sides. What did I just do? Minus 8 equals 0. And that looks factorable, which is good news for us. This is x minus 4 times x plus 2 equals 0. And now we get x equals 4 and negative 2. Now, what we have to do is check and see if anything's extraneous. Check the original problem. Can I plug in anything? Negative 2 would be an issue. That's log base 2 of negative 2, log base 2 of negative 4. If any one of them is a negative or 0 inside your log, that leads to extraneous solutions. 4 is good, log base 2 of 4, log base 2 of 2. And actually, if we double check that, log base 2 of 4 is 2. Log base 2 of 2 is 1. And 2 plus 1 is 3. So that's one I can do without a calculator even, which is kind of nice. All right, number 34. Anyway, negative 2 is extraneous. I don't know if it'll always be the case, but we're definitely going to have to check on it. Log base 6 of 3x plus log base 6 of x minus 1 equals 3. They have the same base, so we can condense these into a product. This becomes log base 6 of 3x times x minus 1 equals 3. It's at this stage we rewrite in exponential form. That becomes 6 cubed equals 3x times x minus 1. 6 cubed is 216. We're going to distribute this guy here and subtract 216 over. Now these can all divide by 3. 72. And that's factorable to negative 9 and positive 8. So x equals 9, x equals negative 8. Now, once again, check for extraneous solutions. Looks like negative 8 will not do. It's more likely than not that the negative answer will be the one that's extraneous, but you have to check on what's actually happening in the original problem. Not always, but if they design the problems the way that they want to, then maybe always. I don't know. We'll see. All right, number 35. Ugh. What are you going to do to us here? Natural log of x plus natural log of x plus 3 equals 4. We condense this into a single log. Note that we have been multiplying these things. So x times x plus 3 is x squared plus 3x. Skipping a little step right there. This is log base e. So if I want to rewrite this in exponential form, this is e to the 4th power equals x squared plus 3x. E to the fourth is not a rational value, so even when subtracting it over, I don't know how factoring that's going to go, right? That's probably not something that goes out cleanly. So here is probably where we got to solve with quadratic formula again. Discriminant is going to be b squared minus 4ac, which is 9 plus 4e to the fourth power. I'm just going to leave it like that. Now, this goes inside the square root of your quadratic formula, but it would be unwise to think that the square root of 9 plus 4e to the fourth is 3 plus 2e squared. That's not how it works. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, 2 times 1. So we're just going to write it like that, and then I'm going to calculate those. So give me a second. I have negative 3 plus, I need parentheses, negative 3 plus the square root of 9 plus 4e to the fourth, close parentheses. Sorry, I have things I'm writing here. I'll show you what I'm writing. So I got that going on. Got 3 sets of parentheses to close there. So the first one is this number, and then I'll do minus for the second number. And we'll have to check on these just by their nature. I'm not going to plug them in. I just want to see if anything results to negatives. So I'm sure the negative one will result to negative logs. So x is about either 6.040 when rounded, or x is about negative 9.040 when rounded is what I'm getting there. So in terms of double checking these answers, that negative 9 one won't be working out for us because that'll get logs of negative numbers from the original problem. So just the 6.040 is the only one that I really care for as an answer. Okay, number 36, another natural log thing, probably another quadratic formula set we're going to do. Or maybe, actually, we might be able to complete the square on this one. So natural log of x plus natural log of x minus 2 equals 5. Condense these into a single log. Remember, it is the product of these two inside. So x times x minus 2 is x squared minus 2x. Rewrite this in exponential form. X squared minus 2x equals e to the fifth power. Now, I'm actually in the good stage of completing the square. That's an even number, and I'll leave this on this side over here. So I'm going to say x squared minus 2x plus 1 equals e to the fifth plus 1. That completes the square. This factors into x minus 1 quantity squared here. We get to take the square root of both sides, and we got a plus or minus going on here. X minus 1 equals plus or minus square root of e to the fifth plus 1. So x equals positive 1 plus or minus e to the fifth, square root of e to the fifth plus 1. So here's our exact. I'm going to be calculating that. 1 plus this and 1 minus this. And I'm getting 13.223 and negative 11.223. Does negative 11 work? No. Get a negative set of natural logs there. No good on that. So 13.223. All right, number 37. Out of the natural log chute, maybe we're getting back to normal, rational answers. Knock on wood for that one. Number 37, log base 3 of 3x squared. Notice that's already quadratic. Plus log base 3 of 3 equals 2. The good news about that being quadratic already is that when you square it, when you square negative answers, they'll turn positive automatically. So unless they're imaginary numbers, all should be good here. So we will condense this, though, into a single log. So we can do, well, actually, listen, log base 3 of 3 is 1. I'm going to do this a little bit differently. Log base 3 of, actually, I'm going to do it much differently here, too. I'm going to separate these. Log base 3 of 3 plus log base 3 of x squared. I'm actually going to expand to contract. Both of these are 1. Log base 3 of 3 is 1. So I'm doing it a little bit differently. You can do this more than one way, of course. And 1 plus 1 is 2. Aha. This is interesting. Plus 2 is 2. It's going to turn into 0 when you subtract. Subtract 2 from both sides, you'll get 0. So log base 3 of x squared equals 0. The only way that's possible is if x squared equals 1. Now, I did my exponential form, 3 to the 0 equals that, but the log of 1 is what gives you 0. X squared equals 1, so x equals plus or minus 1. So that must be the answer set. Now, I did that significantly differently than a previous route of like, if I condense these, make it 9x squared and stuff, probably would have been faster to go the other way. I just wanted to work that out. So let's go just the other way with it. Let's condense this to a single log. Let's turn this into log base 3 of 3 times 3x squared, or 9x squared, equals 2. 2? Yeah, 2. Now, yeah, this is probably faster. 3 squared equals 9x squared. Divide by 9 and take the square root of both sides, equals plus or minus 1. So, looks like that was significantly faster, but I like the idea of expansion. You know, I really like to play with these log things to say that you can as well. I want you to know all the properties and what really calls to mind in some situations when you can work them out. Now, both will work. Both will work, by the way. You can square -1, it turns positive, as well as the positive 1 there. So there's no issue with either answer on that. All right, number 38. Nothing that I can really simplify here. This one is going to make me question what kinds of answers will work, because you can see there's a negative x in there, but this one has to be added to 10 to work. Maybe nothing works, maybe everything works. We'll take a look. So when it comes to distributing here, this is negative x distributing into these, so negative x squared minus 10x. So rewritten in this form is going to be 4 squared equals negative x squared minus 10x. And I'm going to add these over. I want those to be positive. X squared plus 10x plus 16 equals 0, which factors into x plus 8 times x minus 2, times x plus 2. So x equals -8, -2. Interestingly enough, let's take a look and see how these work. Substitute them in. Log base 4 of opposite of -8 is log base 4 of 8. That's good. -8 plus 10 is a positive. That's good. Opposite, all of these should work. -8 and -2. There shouldn't be any extraneous solutions with that one. So while I was saying that, hey, maybe the smaller number is going to be, or like the -2 instead will be that instead of -8, both of them actually worked there. So 2 different answers. Keep it in mind, all good to go. Number 39. Do we get more of those? Who knows? I think the last 2, because they go odd, even, odd, even. I think the last 2 were indicators of, hey, these both work. Maybe this is now a different kind of problem set. Oh, this is a different kind of problem set. All right, so we have to condense these into a single log here. Let's first write it in its factored form so we understand it's this times this. We're going to FOIL, right? In fact, let's do these 2 things in one step. I'm going to get 3 squared to get 9, and here I'm going to FOIL out x minus 9 times x minus 3, and that becomes x squared minus 12x plus 27. Subtract 9 from both sides. And that doesn't factor, right? 6, 3, 9, 2. I don't think that factors. Let's solve by completing the square. I'm going to subtract the 18 over here. This will be 36. Yeah, not a perfect square bit. So this factors to x minus 6 quantity squared. -18 plus 36 is positive 18. Take the square root of both sides. You get x minus 6 equals plus or minus 3 root 2, if I'm going to be a little precise like that. So 6 plus or minus 3 root 2. Now, I still have more to do with approximate answers. We'll see if they work as a whole as far as extraneous solutions go. So I'm going to do 6 plus 3 root 2, which is 10.243 about, and 6 minus 3 root 2, which is about 1.757. So x is about 10.243. X is about 1.757. All right, any don't work? 1.757 will not work. You'll be taking logs of negatives from that one. So the only one is 10.243 from that. 10.243 minus 9 is still, well, it's still big enough. All right, let's go to number 40. Only a little past halfway. I just realized that. I feel like we've been doing a lot of drill and kill, but they still have steps within, right? Log base 5 of x plus 4 plus log base 5 of x plus 1, same base, we can condense them, equals 2. If you notice what happened last time by condensing it, we distributed. So x squared plus 5x plus 4 equals 2. Now, it didn't begin as a quadratic. So, it's not like we can plug it into here to check. We have to plug it into the original. So we will turn 5 squared into 25. So x squared plus 5x plus 4 equals 25. And this subtracting x squared plus 5x minus 21 equals 0. Oh, it's not 7, negative 3. Not factorable. We're going to use quadratic formula for this then. Our discriminant being b squared minus 4ac, or 25 plus, I had it and lost it, 96. Oh, was that factorable? Wait a minute. Oh, I'm sorry. This was not 24. This was 21. This was 21. This was 21. Because that would have been 121, which would have been a perfect square. All right. So 25 plus 84. That's the only reason that I knew that was... That's the only reason why I double checked on that, because I got a perfect square. Otherwise, I would have just gone on with the wrong work. So 109. Not a perfect square. Not factorable. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Negative 5 plus or minus root 109 all over 2. I can tell you the negative answer will not be working for us. Well, as long as the negative answer is less than, isn't greater than, negative 1 or whatever, this shouldn't be working for us. So I'm just going to work off negative 5 plus root 109 all over 2. Negative 5 plus square root of 109. Oh no, I hit the wrong button. Square root 109 all over 2. So I'm getting 2.720 as the only valid answer. I think I need to write the other one anyway, right? When it comes to a test, it's like solve them and then show the extraneity. So let's still figure out the other one and then cross it out. So the other one would have been negative 7.720. And that doesn't work. It's too small as far as getting positives from the original log stuff. All right, there's that block of problems. Let's move forward. Numbers 41 and 42 describe and correct the error in solving the equation, both logarithmic equations. Number 41, log base 3. Okay, I see the issue here. Log base 3 of 5x minus 1 equals 4. Now, assuming everything they did after is fine, which is good, the error is the step in right here. Now, there's nothing wrong in how they're approaching problem. If they'd like to raise them as 3 with, 3 with both of those, that's fine. But I'm going to write it first and then I'll describe it. Log base 3 of 5x minus 1 equals 4. What they want to do in this case here is they're attempting to write it like this. Raise these as exponents with a base of 3. The problem is this side doesn't have a base of 3. So the right side of the equation have the base and exponent swapped. So let's continue on that. Now, it's natural for you to have this because 3 to the log base 3 of 5x minus 1 is 5x minus 1. So that becomes 5x minus 1, and this becomes 3 to the 4th, which is not the same as 4 cubed. 3 to the 4th is 81. So you add 1 and divide by 5, you get 82 over 5, which I think is also 16.4. So this, that, or the other thing, that is your number 41. Number 42. They're going into condensed mode here. They have this same base. They multiply those out. They do the base raising there. All looks good. 4 cubed is 64. They distribute. They subtract 64 over. And this factors 16 times negative 4. And that's good. Negative 16 and 4. I guess the issue is the answers. One of them is extraneous. So listen, all the work looks great. All the work looks great. The only problem is, and this is going to be very straightforward as far as correcting, negative 16 is extraneous. The work is correct. But x equals negative 16 is an extraneous solution. So all they had was good. If you want to follow textbook work, no pun intended, that is what they do. So the final answer, as far as correcting it goes, I'm going to cross out that negative 16 in red. And I'm just going to box x equals 4. Boom. All right, I trust all the rest of the work's looking good. Normally with the error things, there's only one thing that's wrong, and that seems to be the wrong. All right, number 43, problem solving. You deposit $100 in an account that pays 6% annual interest. I like these questions. How long will it take for the balance to reach $1,000 for each frequency of compounding? Oh, there are 4 different ones we're going to do here. All right, there are 2 different kinds of formulas we're going to play with. There's this one for annual compounding. There's this one for compounding based on n times throughout the year. And there's this one for continuously compounding interest. So part A is going to use A. You compound once, so n is 1 in this case. So annual, according to Lloyd Christmas and Dumb and Dumber. Host annual. Okay, $1,000 is the accrued amount. $100 is the principal amount. Now here's the thing. This is always going to be the principal, and that's always going to be the accrued. So there's something I could do with that each time on these problems that I'm going to simplify actually probably up here in just a bit. This is 1 plus, now our r is always 0.06, but this won't always simplify because each equation type is different. So how long will it take to reach this? T is what we're trying to solve for. Now 1,000 divided by 100 is 10. So I want you to note that each time that we do these here, we can just write, because we're just asking how long will it take to make our money 10 times more than it was. Doesn't matter what the money is. We're just saying it's now 10 times more. So 10 equals, this is, I don't need parentheses, 1.06 to the t power is our setup for this one. Each setup will have 10 equals something if I truly want it to. That's going to work itself out just fine. Now I can log. This is where, do I want to log with 1.06 as my base? Not necessarily. Some of these bases can get a little funky looking. This is where you might just want to log both sides in the common log way. This is where it might make more sense to write it like this. Now, when you do that, first of all, the log of 10 is 1, which is great. But also, t multiplies by this log of 1.06. It comes out and comes down that way. So t is going to equal 1 over log of 1.06. So I'm going to go ahead and figure out what that is. 1 over log of 1.06. 1.06 is more than 1, so that should be a positive result. All good there. 39.5 years. And t is in years. It's not in minutes like the cooling rate, Newton's cooling method problem, whatever it was. So there's the annual answer there. Now part B is quarterly. That means for quarterly, we're going to use the middle formula where n equals 4. We're going to compound 4 times, but we also have to divide 0.06 by 4. So we're going to use it this way. Now 1,000 equals 100 times whatever. Divide by 100, you still get 10. So I'm going to save a step. Actually, I'm not going to, because I don't want you to ask where this came from and didn't. Plus, I have to simplify the inside anyway. But I could have. I could have just written this as 10 equals, and the next step I'm going to do that. So this is 0.06 over 4 raised to the RT power, to the NT power. 4t power, like that. So there's more simplification to be had as an overall bit. I am going to divide by 100 and get this 10. 0.06 over 4 is 0.015. So I can rewrite this as 1.015. That's kind of simplification there. I don't need parentheses, just like last time. And it's at this stage that I can, again, log both sides. So you can see there are some common traits going on. When I log both sides, log of 10 is still 1. So I'm still getting a 1 from this no matter what I do on this set of problems that I'm doing. Now this is 4t times the log of 1.015. I can do one final division to solve for t, but notice that it's not just going to be log of 1.015. 4 can also be a part of that division. So both of them together in the division is going to look like that, a little bit different. Now, I don't know the answer. All I know is it should take less time for quarterly than it should for annual, given everything is the same. Quarterly compounding versus annual will be more money over same amount of time or less time for same amount of money. And same with daily coming next on part C. So when I do my calculation here, keep in mind that the 4 needs to be in parentheses with this other guy here. I should do 1 over 4 in parentheses times log of 1.015, like that. And it is less time, not significantly less, but it is less time. So I'm trusting my work so far in my answer. This is 38.7 years about. Or as I wrote, yars. Our pirate compounding. The amount of yars. It's a wink. Part C is daily. Daily, we're assuming a non-leap year. N is 365. Look, if you do 366, round it to one decimal place, I don't think it's going to change your answer. So this is going to be, once again, $1,000 accrued equals, take the 100 principal times 1 plus 0.06 over 365 raised to 365t. This one's going to be a little bit different because I don't think 0.6 and 365 have like a, or 0.065 and 365. I don't think it's a clean number through dividing. It's not at all. So I'm going to leave this kind of separated like that. Remember, I still have 10 on this side, 10 on this side, and this is just going to look a little hectic. You don't want to do any early rounding. I want to keep stressing that over and over. What we type in the calculator is going to be very paramount to what we do here. This is where I am going to log both sides. Log of 10 is still 1. That has not changed. So logging both sides here, so I get 1 equals, now I got this whole thing, but it's multiplied by 365t. Remember, that's 365 times t. I bring that up because when I do this entire thing, I'm going to divide by all that. So I'm going to divide both sides by 365 times the log of 1 plus 0.06 over 365. It pretty much looks like I just did that now. So let's do 365 times. So let's go to the calculator. This is what I'm going to type out right here to solve for t, right? Because those are gone. Those are gone. Now the time here, it's going to be even less time than the quarterly compounding. Maybe we're around 37 years at this point, or at the beginning end of 38 years. I don't know. Let's go to the calculator for that one. I'm going to do 1 divided by, and in parentheses, 365 times the log of, and in parentheses, oh, they already have parentheses here, 1 plus 0.06 over 365. You don't have to close parentheses here, but I tend to make it look good. It's still in the 38-year range, so 38.4 years. A few months before the quarterly compounding. Is it worth it? I don't know if there's a trade-off, but that's the answer. The last one is continuously. So this is where we're going to make n be infinity. Kind of, not really. I'm actually just kidding. We're going to do, this is number 43 still. This is where we're going to use apert. So part D, continuously compounded interest. So this is A equals PE to the RT. All right, 1,000 equals 100 times E to the 0.06t. A little bit cleaner looking. Divide by 100, you still get 10. Because E is a better log for what we're going to do here, I'm just going to natural log both sides this time. Boom, boom. And natural log of 10 is not 1. Natural log of E to the 0.06t, however, is 0.06t. So we'll divide both sides by 0.06. And let's get that result. So natural log of 10, this is going to be the least of them. It's probably still going to be in the 38 range. Let's see. Natural log of 10 over 0.06. It's still even, it's, check this out, to decimal places here. Listen, they're diminishing returns ultimately. Does it take less time? Yes. It probably takes a few hours less than it does from the previous one. So the time, because this is in, no, I'm sorry, a few hours less. Maybe a day or two less. I don't know. But I'm still going to say 38.4 years. I hope in the last one I also said 38.4. I hope I did round up. But it is less. Insignificantly less, but it is less. All right, number 44. Modeling with mathematics. After this, I think I need a quick break here. Modeling with mathematics. The apparent magnitude of a star is a measure of the brightness of the star as it appears to observers on Earth. Apparent magnitude. The apparent magnitude m of the dimmest star that can be seen with a telescope is m equals 5 times log of d plus 2, where d is the diameter in millimeters of the telescope's objective lens. What is the diameter of the objective lens of a telescope that can reveal stars with a magnitude of 12? So we're going to set 12 equal to this and start solving for d. Remember, log is log base 10. Keep it in mind when we do everything in the end. Subtract 2. Divide by 5. And rewrite in exponential form. That's 10 squared. 10 squared equals d, or 100. Diameter is in millimeters. 100 millimeters. That is the diameter of the objective lens in that case. So it wasn't solving using logs, it was solving a log equation. A little different story. All right, 1 second here. Okay. Is that the bottom of the page? Yes, it is. Okay. All right, number 45, analyzing relationships. Approximate the solution of each equation using the graph. So we have 1 minus 5 to the 5 minus x power equals -9. This is part A. So what they do is what you're supposed to do when solving these equations. You make y equal each equation separately, and you find where they intersect for the x value. So where they intersect, the x value here, notice this goes by scales of 2, 2, 4, 6, 8. So this is somewhere between, here's 3. It's somewhere between 3 and 4, maybe around, I don't know if that's around the 3.5 mark, 3.5. I'd say probably 3.6 or something like that. I don't know. I'll just say x is about 3.6. That's going to be my answer there. Maybe 3.7, maybe it is 3.5. But somewhere in between 3 and 4 looks to be the case for that one. You can probably make a different argument. We can actually solve it, right, using logs and such, but I'm going to leave it on that one. Part B, log base 2 of 5x equals 2. Well, this one I can kind of cheat with because I already saw this. I know this answer in my head. You might as well if you do some work here. So this is kind of going to be cheating here. But you can see where these two things intersect here. This is increments of 1, so that's 1 and stuff. And, you know, when you see that part where it crosses, I'd say that's about, let's see, I'd say that's about 80% of the way from 0 to 1, you know, about 80%. So I'd say x is around 0.8. You know, no reason to think that, just around 0.8. Yeah, in my head, I automatically went to 2 squared equals 5x. So divide 4 by 5 and you get 0.8. So that one, I kind of cheat on my own. The other one, I didn't even bother trying in my head, and I don't think I could do in my head. So I don't know what part A is. Part B is 0.8. So yeah, I don't know what an answer key thing would say if they're like, you know, it's around 3.714 and like they have the exact answer. So I don't know. All right, anyway, number 46, making an argument. Your friend states a logarithmic equation cannot have a negative solution because logarithmic functions are not defined in negative numbers. Is your friend correct? Justify your answer. No, your friend's incorrect. In fact, we saw negative answers for one of them. It was like -2 and -8. Your friend is incorrect. It's not that we can't have negative answers. We can have negative answers as long as they do not produce logs of negative numbers. Same is true for positive answers. If I have an answer that is x equals 2, and in the log it says log of x minus 5, well, 2 minus 5 is -3. X equals 2 won't work. So your friend's incorrect. You can absolutely have them. We actually even saw some. Let's go back and find them. There was the plus or minus 1 answer right there. So -1 was an answer. And yeah, this one, the -8 and -2. It works out. I can plug -8 in here and -2 in here, and they all work out. So maybe it was after having done that problem that we can make sense of that answer. But sorry, friend. We just got to make sure that we double check our answers with those anyway. All right, numbers 47 to 54, we're going to solve the inequality. And it looks like a lot of other mumbo jumbo down below afterward. Now, solving the inequality, states that as long as our b, and I'm just going through all the problems first right now. As long as our b value is more than 1, which it is true on 47, 48, 49, 50. So our b value is more than 1, then whatever the inequality states for now will hold true when we end up solving it, which means like if I log both sides right now with base 9, which is my best way of solving for that one, then the left side will still be greater than the right side in this case as well. X will be greater than log base 9 of 54. Now log base 9 of 54 is the exact number, but I want to do log of 54 over log of 9 to approximate this. And I don't know how to say approximately greater than or greater than approximately, so I'm just going to put the greater than like this. So log of 54 over log of 9. Log of 9 is 1.815 approximately. So either or, I don't know which one. I think they've been doing a lot of rounding in the examples, so I'm going to stick to rounding on probably all of these. Just understand they are approximates this time. Number 48 is 4 to the x power equals 36. I'm inclined with both of these numbers because they have factors of 4. I'm inclined to do extra work on these to like work it down in a smaller log case, but because we're stealing log base 4 of these, I think we're good. Trying to think of what I'd say on that, but I'm going to leave it. So x is going to be less than or equal to this log base 4 of 36. So I got to do log of 36 over log of 4, or natural log, whatever. Log of 36 divided by log of 4. 2.585. Now, I should be making sense of these answers for you guys here. I should always say, yeah, that makes sense because. So let's go to this one. We'll go back up to the top. 4 squared is 16. 4 cubed is 64. So being between those two for 36 makes sense. 9 squared is 81. 9 to the first is 9. So being between 1 and 2 makes sense for that one. I'm feeling it. Now, regarding these questions, there is no restriction on what we can plug in for x for exponential functions, domains of all real numbers. Logarithms, on the other hand, are a little bit different. Number 49, natural log of x is greater than or equal to 3. There are a couple things I got to say on this problem. Let's begin with the domain. Let's not forget what it is that, would be restricted information, because we're not just solving for a single x and saying plug it in, we're solving for an entire range. So for one thing, x must be greater than 0 no matter what we have. So if this is a bottom end that we have to write, ultimately, we're going to do that. Second thing is this, we've always been saying this rewrite in exponential form. So in other cases, because it's base e, I would say e cubed equals x and stuff like that. But in the case of this, we have an inequality. So this is a little tougher as far as saying which way does this thing go when I'm rewriting it this way. So what's best to do here is use that other property where we're saying use e as your base, raise it like that. E to the natural log of x is x, and therefore the greater than or equal to goes this way. E cubed is on this side like that. So x is greater than or equal to e cubed. Now that's a positive number, so the greater than 0 is not actually going to even apply to our stuff. Don't worry about it. But e cubed is around 20. Oh, I know that, 20.1. 20.086. 20.086, which of course is greater than 0 as well. So you're all good on that set. As long as we're there, we're good. Number 50, we have log base 4 of x is less than 4. Log base 4 of x is less than 4. So once again, you probably want to write this with this base right here to make sure you know which side these things go on. 4 to the log base 4 of x is x, and 4 to the fourth, which is 256 by the way, is on this side. So x is less than 256. But what do we state about the other set? It needs to be a positive number still. So it needs to be greater than, not 10, it needs to be greater than 0 as well. So it needs to stay within those two parameters. If it ain't no good. Less than 256 keeps it under 4. Greater than 0 keeps it functional. Keeps it defined as a value. We're back to exponential functions on number 51. So 3 to the 4x minus 5 is less than 8. Now there are no domain restrictions in this scenario, so we're good there. I should probably break this up a little bit. Give me 1 second. As always, probably faster to just rewrite it. 3 to some power cannot give me 8 naturally, so we're just going to log base 3 both sides right now. We'll do some extra solving stuff. So we got 4x minus 5 is less than log base 3 of 8. We have to add 5 and divide by 4. So 4x is less than log base 3 of 8 plus 5. And divide by 4, x is less than log base 3 of 8 plus 5 divided by 4. So when you type this in the calculator, because I don't know what that number is, this is going to be less than a yeah, this makes sense kind of thing. I'm going to kind of estimate it. Log base 3 of 8 is really close to 2, a little bit less than 2, but it's really close to 2. 2 plus 5, really close to 7, just under 7. 7 over 4, around 1.75. I'm going to say it's going to be around 1.7 or so. But what we need first is a set of parentheses to open with for the numerator. Okay, we're going to do log of 8 over log of 3. I'm closing just the parentheses set for that. Now plus 5, and then close the parentheses for the numerator. Where's the plus? Close the parentheses for the numerator, and then divide that by 4. If I get around 1.7-ish, I'll feel good on it. 1.723, feeling good on it. So x has to be less than 1.723. Now, any number is good here for domain because it's an exponential function. Number 52 feels very identical. Maybe a little less work because we get to hit natural log on this one. No, it might be the same work. It's greater than 11. Let's natural log both sides right now. So we get 3x plus 4 is greater than natural log of 11. Subtract 4. And divide by 3. I want to remind you, by the way, that these are only going to stay the same way for these inequalities because our bases are 1 or are greater than 1. If they were between 0 and 1, these inequalities would actually have to flip, but we're not doing that in these cases here. All right, natural log of 11 minus 4, all in the numerator, and then divided by 3 gives me around negative, and I wouldn't have anticipated this, negative 0.534. Okay, let's say that. Any answer will do for an exponential function. Numbers 53 and 54, however, these are going to be logarithms, so we have to be more careful for what kinds of solutions that we have. Let's take a look. So on number 53, we have negative 3 times log base 5 of x plus 6 is less than or equal to 9. You need to get this log function by itself on its own side of the inequality. We'll subtract 6 from both sides. And then we'll divide both sides by negative 3. Now, dividing both sides by a negative in an inequality will flip the inequality. So this becomes greater than or equal to negative 1. The same rules apply for what we want to take care of here. We're going to raise these with a base of 5 like that. This becomes just x. It's still greater than or equal to here. And 5 to the negative first power is 1 over 5. Now, all of these will remain positive numbers, so we're good. Remember, within this domain, x must be greater than 0, and this is greater than 0 for here. So that should be the set. We're good on number 53. Number 54, we have negative 4 times the log base 5 of x minus 5 is greater than or equal to 3. Looks like another dividing by negative is going to happen here. Let's first add 5 to both sides. And we'll divide by negative 4. This will flip our inequality from greater than or equal to less than or equal to. So less than or equal to negative 2. And let's still apply that 5 base as we had previously like that. So this will become x is less than or equal to, and 5 to the negative second is 1 over 5 squared, which is 1 over 25. So this would be the answer set, but we have to also stay positive. So we have to stay greater than 0. So the other portion of the inequality is right here, but greater than 0. This is a very, very small window of values that we can be. Anywhere between 0 and 1 over 25, 0 and 0, I think 0.04. It's an infinite number of values, but that is a very small range for which things are true. That's an interesting set there. It's not greater than for very long. All right. Number 55, comparing methods. Let's solve log base 5 of x is less than 2 algebraically and graphically. Which method do you prefer? Explain your reasoning. I prefer algebraically because it's easier and quicker. So let's start with algebraically. Log base 5. There's no world in which this is a better thing to solve graphically, even with the graphing calculator. That being said, I'm going to solve it. Maybe we have to use the graphing calculator. I don't know. We can do the 5. We can do the 5 thing right here. And this is x is less than 25, but it must be greater than 0 here as well. Right? Between 0 and 25. There's the algebraically part. Graphically, a couple things I can mention here. I'm going to do my own graph. I'll confirm with the graph on the thing, but I need you to see kind of what they look like. And it goes to 25, so my graph thing doesn't really go. Let's go by 2s here. So this is 10 and 20 and 30, like that. I'll still go by 1s on y. So I have a vertical asymptote at x equals 0, which goes to show that we must be greater than 0 for these points of the graph here. This is log of 1 is 0. Oh, that's not 1. That's 2 now, huh? Log of 1 is 0. As we increase y by 1, we go times 5 here. Increase by another 1, it's another times 5 at 25. And that's kind of all I can fit there as we divide by 5 and go this way. So this must be greater than 2. Excuse me, less than 2. Less than 2. So for what values is this graph? Let me do that again. No. All right, what values is this graph less than 2? So here's y equals 2 coming up. Remember, we were basically graphing y equals and figuring out where one goes versus the other. I'm going to thin that out. Okay, so this is the point of intersection at 25, 2. So when x equals 25, then boom, they are equal. When x is greater than 25, this blue is above the green, so that's when it's greater than. This is when it's less than here the entire time all the way through 0. Now it can't be 25, otherwise they're the same. It can't be 0 because it doesn't fit within the domain. So right here, anywhere between 0 and 25, it still works out. So the blue is under the green from 0 to 25 on x. I don't have much to say on the graphing calculator portion. We did the graph there. I prefer algebraically. Justify, it was just faster. I can get decimal answers that way. I'm going to remember the domain portion personally. I mean, it's just a methods thing. Maybe there are different problems where graphing's going to be better. Not that one. Number 56. You deposit $1,000 in an account that pays 3.5% annual interest compounded monthly. When is your balance at least $1,200 and $3,500? So, $1,000 deposited. Now, first of all, we're going to be using this formula here. Compounded monthly, we're going to be talking about 1,000 deposited. We have 3.5% monthly. And we're talking about the when. When is your balance at least $1,200, at least $3,500? We want, so I'm going to say part A for 1,200. We want this side, given a certain time, to be more than the 1,200 or equal to. So at least, so less than or equal to, like that. This is how we're going to write this one out. 1,000 times, I don't think 0.035 over 12 cleans up. Let's see. Sadly, it does not. So we're going to say 1 plus 0.035 over 12 raised to the 12t power. And we're going to have to do some, division, stuff like that. Divide by 1,000. We get 1.2. Now, this is one of those problems where I believe I'm going to go kind of fast on the next set when it's 3,500. I just got to divide. I'm going to turn it into 3.5 instead. So whatever we're doing here, we're also going to do for the next problem. I'm going to log both sides as is. Just log the common log, like so. And 12t comes on down. Come on down, 12t. we have log of 1.2 is less than or equal to 12t times the log of 1 plus 0.035 over 12. Now we divide both sides by 12 times the log of that. So t must be greater than or equal to, the time must be greater than or equal to log of 1.2 divided by 12 times the log of 1 plus 0.035 over 12. So the difference between this problem in part A and part B is this will say 3.5 instead of 1.2. So I'm going to go pretty quick on the second one here. Now the first one, I have log of 1.2 divided by, use parentheses on the bottom, 12 times the log of 1 plus 0.035 over 12. And I'm getting 5.216. T must be greater than or equal to 5. And I really got to round up here in some sort of way. So I'm going to say 5.217 years. This is in years. We have to be more than that. Maybe they say 6. Maybe they say 6 years. It needs to be more than 5 for sure. Between 5 and 6, but in that set. Now part B is 3,500. Straight up, guys, I'm going to be doing this exact same equation that you saw right here, only instead we're going to be using 3.5 because 3,500 divided by 1,000 is 3.5 instead. So here we get to just say this. I'm going to go in the calculator, change the 1.2 to a 3.5, and we should get our answer from that. That's efficiency, folks. No reason to do the exact same work to get the same answer. So 35.845 years. Now that was rounded down, but because it's a greater than or equal to, I don't really know what to say on that. I'm just going to go and keep it like that. Maybe they say 36 years. I don't really know. But that's just the idea and what we want to say on a problem like that. Okay. All right. Let's go to number 57. Problem solving. An investment that earns a rate of return R doubles in value in t years, where t equals natural log of 2 over natural log of 1 plus R, and R is expressed as a decimal. To take home, because these are the kinds of math things that I'm like, yes, I agree. That's how that thing works. You know, let's say it says if something doubles, right? Say that you invested $100 and now you want $200 out. Now we're using, this is just an annual thing that they're talking about. So this is just 1 plus R to the t power. So what do they do to this problem? They divided both sides by 100 right here. Then they natural logged both sides. You can log both sides, natural log both sides, your call. And when you natural log both sides here, we have the t that gets grounded right here, t times natural log of 1 plus R, and then you divide both sides by natural log of 1 plus R. So you get t equals natural log of 2 over natural log of 1 plus R. So there's their formula, right? It comes from something. It didn't have to be 200 and 100, by the way. Whatever divided by something else, something dividing from something that's double it will always be 2. I was giving an example of 100 and 200. Could be 1,000 and 2,000, whatever. Anyway, what rates of return will double the value of an investment in less than 10 years? So they want the t, they want the t here. We want this thing to be less than 10 years. That means we want 10 to be greater than that rate of return. So we want to solve for R in this case like that. All right. We're going to multiply both sides by natural log of 1 plus R. So we get 10. Let's see. Should I do that? Yeah. So I get 10 times natural log of 1 plus R is greater than natural log of 2. I can divide both sides by 10. And we get, now we're moving here. I'm going to write this a little better here now. Natural log of 1 plus R is greater than natural log of 2 over 10. And now I can raise both sides, you know, like do the E thing right here. And this just becomes 1 plus R on this side is greater than E to the natural log of 2 over 10. Don't try and simplify that just given what it has. You could rewrite it as some sort of things. Like I think the 10th root of 2 is a proper thing that we can write. And I can double check that afterward if you'd like me to. But R is greater than here, E to the natural log of 2 over 10 minus 1. This is a requirement for R. So first of all, I want to check that decimal, and then I do want to see if the 10th root of 2 minus 1 would give me the exact same result. I'm actually very curious now. So R e to the natural log of 2 divided by 10. This is all in the exponent, and minus 1 gives us this rate of 0.717. So R has to be greater than about 7.2%, just so you have the heads up there. 7.2% as I do a rounding. Let's go back to the calculator. I'm really curious to see if I can do the 10th root of 2, or 2 to the 1/10. 2 to the 1/10 minus 1 and get the same thing. What did I just do here? Pi. There we go. Yeah, same number. So I could have done some different things there, but I'm good. I'm good where I'm at. All right. Cool. Number 58. Your family purchases a new car for $20,000. Its value decreases by 15% each year. During what interval does the car's value exceed $10,000? So your principal amount, this is kind of an accrued amount thing. Normally they use different numbers here. They'll use y in a lowercase a for, this is the formula they kind of give in this case. Because this time it's plus or minus, and it's not always interest. They don't talk about accrued if it's not gaining money. So the y here is $10,000. We have to stay above 10,000, exceed it. So 10,000 must be less than what we're doing with our $20,000 car investment. The value is decreasing 15% each year. We have to find the value of t that works this out. Now, the minimum for t is, of course, 0. It goes from 0 years onward. So we're going to have to figure out what t we stay underneath for that. If we divide by 20,000, this turns into, of course, 1/2 or 0.5, whichever way you'd like to put it. I'll place 0.5. Oops, I'm not doing log just yet. I will do log. But this is 0.5, which is less than, this is 0.85. 0.85 to the t power. We will now log both sides. I command you to log, like so. And that'll become t log of 0.5 is less than t times, sorry, I was thinking of different ways that I could say, or we could rewrite it this way and this way. I'm always infatuated with doing different ways of writing the problem. I feel like this time it's going to be a little too much overkill to state. Let's just solve this problem here. If I divide both sides by log of 0.85, t will be greater than that. It's still greater than. So log of 0.5 over log of 0.85. Now, both of those are negative. When divided becomes positive. So t is greater than, hold on a second. During what interval does the car's value exceed $10,000? I'm sorry. We want our value, should it be less than? I feel like I'm doing something backwards there. If it exceeds 10,000, you know what it is? This is actually really interesting, and I'm just recognizing this now. We're technically dividing this. This is interesting. Okay, we're technically dividing both sides by a negative number. Log of 0.85 is a negative number, so when we divide by a negative, guess what? We actually flip the inequality. Okay, because I was saying this should be a less than value ultimately, right? And it should be. And I'm not forcing this. We're dividing by a negative. That's interesting because I obviously don't round until the end. But that's a negative number. Oh my gosh, that is really interesting. Okay, so we don't see it as a negative, but it is, so the inequality flips. Remember, t was on the right side, so I put it on the left side. That's what made me flip it, and now we're flipping it over that way. Okay, that makes more sense to me. Okay, so let's do log of 0.5 divided by log of 0.85. And you know what? Me doing it another way that I was thinking of being clever with my writing would have actually revealed that, because it would have given me negative answers. So this is 4.265. T is less than 4.265 years. So it needs to be within, it says during what interval? Between 0 years and 4.265 years. Obviously from when it starts to then. It's still above $10,000 at that stage. Okay, numbers 59 to 62. Use a graphing calculator to solve the equation. Fair enough. They requested it. We shall do it. Not inequalities, they're just equations. So we'll go straight into it. We're going to set y equals for both of these. Let's say I can call this y1 and y2. We want to see when they intersect. I don't know when. And in fact, it's probably better to do these because I don't know how to solve a natural log versus an exponent here and there. I'm sure if I work it out enough, I'll know what to do. But otherwise, this is why they're asking for the graphing calculator. So natural log of 2x is there, and 3 to the negative x plus 2 is there. Okay. Let's check the window and see what's going on. All right, so that's where they intersect. So I'm just going to go to calc, intersect. Here's my first and second curve. Oh, wait, hold on. It's not, okay, here's my first curve. Here's my second curve. When they say guess, says find the point of intersection. It's going to be right here. This is our x value at about 1.782. So we're going to do these for all 4 problems here. I think they'll be fine unless they show a no solution, something. We're just finding the x value for which that'll work. You can double check it. I'm going to go ahead and trust it. Number 60, I have log of x equals 7 to the negative x power. Again, y1, y2 will suffice for us. So I'll go back to the calculator, do the same thing. Log of x and 7 to the negative x. All right, let's see. Is that small guy and that small guy? Oh, geez. I can't tell what it's doing. I mean, it's a decay, so it's intersecting right within there somewhere. I'm sure some zoom in would help, but it should be intersecting once, just a standard exponential function. So where do these guys intersect? I got to go a little bit right there and figure it out. Okay, it's about 1.233. Okay. There you have it, 1.233. Number 61, same log of x on this side. And then we go back to natural log of 2x. I should have looked beforehand and seen what was going on. I seen it. All right, 3 to the x minus 3 power. And I know to anticipate what kinds of answers we'll get here. To me, they're whatever. I'm just writing what they give me. X minus 3. I think they're just trying to make sure you know how to use features on your calculator. In order of operations. Ooh, this might intersect more than once. Let's take a look. The other ones wouldn't have because they didn't curve. They didn't both increase together. These ones do. So this might increase here or go through and then hit a second time. Oh, I cannot tell. I'm going to have to zoom in a couple times here, guys. This is where we're practicing some more features here. I might have to change my scale, my window even. Instead of zoom, I might just... Here's the log curve. And here's 3x minus 3 curve. Dude, I still can't tell. It might intersect. Listen, it might intersect once is great. I need to know if it intersects more than once. So what I'm going to do here, what's my window? I need to pinch my y's much more than I am right now. Where am I between? I need to go kind of right in that middle area between like 0.2, 0.2 and 0.4. Really pinch that thing up, squeeze it up, because I need to see what's happening in between here. Oh, I don't think they touch. I don't think they touch. So let's go all the way back out. I'm going to do my negative 9.4 stuff. I thought they maybe touched twice. Maybe they don't touch at all. So let's just zoom back out, make sure they hit every part where it could have possibly hit, and I'll ask for intersection. If it says like error or whatever, I forget what it says when they don't intersect at all. But let's go to intersect now. I wanted to make sure it didn't hit twice, and it looks like it might not hit at all. Let's see. I don't think they intersect. If it's still loading like that, then they don't intersect. So I'm going to start writing no solution. I think eventually it says something like error, no intersection, or no sign change. That's a way of saying no solution. So no solution for that, when I thought there were maybe two solutions. Maybe the next one will have two solutions. No value of x really ever makes that true. Cool. Number 62. Natural log of 2x equals e to the x minus 3. Maybe more of the same. Let's see. So still x minus 3 inside, right? Yeah. 3 to the x minus 3, e to the x minus 3. Okay, let's see this one. All right, that one clearly intersects twice, right? That is clear as day. So we got to find both bits of intersection. So here's what you're going to do. Select the first curve and the second curve. When it says guess, whenever I guess, it's going to find the first intersection right here because that's closest to where my thing was, so that one. So there are two different solutions. There's 0.545. I'm going to write it off screen. 0.545, and then I'm going to do it again. Intersect. First curve, second curve, and when I guess here, I got to get closer to the other solution. So I got to go around here, and then it's going to find the other one. So the other one's going to be about 3.693. So two solutions that time. Kind of what I expected, because that's the last two got a little tricky. All right, so that's solving by graphing. Solving using the graphing calculator. Number 63, rewriting a formula. A biologist can estimate the age of an African elephant by measuring the length of its footprint and using the equation L equals 45 minus 25.7 e to the negative 0.09a. L is the length in centimeters of the footprint, A is the age in years. Rewrite the equation solving for A in terms of L. So we're not plugging anything in. We just got to get A by itself now. I have to first subtract 45 from both sides. Divide both sides by negative 25.7. Now, as a personal note, I do not like negative denominators. So I'm going to distribute the negative to the top, make the 45 positive, the L negative, and have 25.7 on bottom. Is clearly nothing will also simplify in that way. So that's a personal thing. I'm going to now natural log both sides, getting rid of that E completely. The LN and the L are completely unrelated L's. Keep that in mind. This is negative 0.09a equals natural log of 45 minus L all over 25.7. You can also do forms of expansion of that. You can put a subtraction. I'll kind of show you what I mean here. And divide both sides by negative 0.09, so A can equal, I'm going to put negative kind of on top. So negative natural log of 45 minus L over 25.7, all divided by 0.09. Now, dividing by 0.09, I don't think there's a good way of stating that's also multiplying by this, because it's like 1.1 repeating. I guess, is it 1.1 repeating or 11.1 repeating? 1 divided by 0.09. Yeah, 11.1 repeating. So there's no good version of that. Unless, well, that's also, hold on. It's a fraction. As a fraction, it's 100 over 9. So I can do this. So there are a lot of things I'm going to do to kind of patch this up. It's probably no worth it to you because we're just supposed to plug something in. I just like to play with properties of rules and stuff. Dividing by 0.09 is multiplying by 100 over 9. So I can write negative 100 times natural log of this. 45 minus L over 25.7 all over 9. Nothing should change and affect my answer. And if you don't want a fraction within your log, you can also have negative 100 times the subtraction of two logs here, like this. I know at this point you're like, yeah, this is overkill like that. And distributing the negative 100, then I can put, I'm going to make this first term positive now. Positive 100 times natural log of 25.7 minus 100 times natural log of 45 minus L all over 9. That to me is a fun looking version of that answer. I can't tell if I'd rather have the 100 factored or distributed, but that should be the same answer as this one when it comes to equation stuff, or this one, what we all wrote. I just like that appearance of that one more on a personal note. Does it help? Not necessarily. Does it have cleaner numbers, not fractions within fractions or extra decimals? Yes, it does. Heck, 25.7, you can turn as 257 over 100. Anyway. Use the equation part A to find the ages of the elephants whose footprints are shown. All right, 36, 32, 28, 24, and they said centimeters for that set there. Okay, so I'm going to go to my graphing calculator. I'm going to write my equation that I put. I sure hope it's the right one after all the work I had. I trust my own ability there. But for you, you might want to plug in the one with the 0.09 in it in case you got lost in the extra stuff that I did. So I'm doing this here. Oh, I didn't put natural log here. Hold on. The answer was wrong. I'm missing a natural log right there. My bad. Okay, anyway. So here, natural log of 45 minus L, or minus X in this case, all over 9. So that's fun. I'm going to ask for certain values here, and those numbers are going to be these centimeter lengths. We'll have 36, 32, 28, and 24. These are the ages of the elephants. So around 2 years, 2.2 years, 4.6 years, 7.6 years, and 11.7 years. Let's go for it. So I'll say A sub, what were my, hold on. I lost my window. Give me 1 second. A sub 36 equals about, these are all approximate. Now I lost my calculator. Equals 11.7 years old. A sub 32 is about 7.6 years old. A sub 28 equals about 4.6 years of age. Yars. And A sub 24 is about 2.2 years. Again, yars. Again, I hope that they are scientifically accurate on that. It's cool information. I won't remember it, but it's cool. All right, number 64. How do you see it? Use the graph to approximate the solution of the inequality 4 times the natural log of x plus 6 is greater than 9. Explain your reasoning. You want to find when the blue's above the red. That's what you're looking for because y equals 9 is the red equation and the other one's the blue one. So when is blue greater than the red? It looks like it's intersecting at 2, maybe a little bit more than 2. It looks to me like it's a hair more than 2. I'm sure if we answered it, it would be like 2.08, something like that. But it's just when x is greater than 2. Let me copy paste the graph just so you can see it bigger and so it has some context when we talk about it on our set. So can you see where blue looks? I'm actually going to zoom in. Can you see where it looks like the blue is not crossing the red right at 2 but more than 2? Maybe around 2.1. So I'm going to say, when is that the case? When x is more than maybe 2.1 is when blue is above red. So I'll say this is about the interval when the blue curve is above the red line. Now I'm very fascinated in the actual answer. So if I subtract 6 and divide by 4 and raise both with the e power there, that's e to the 3/4 power. And e to the 3/4 power is 2.117. So I'm good on my 2.1 answer personally. Okay. Number 65. Write an exponential equation that has a solution of x equals 4. Then write a logarithmic equation that has a solution of x equals -3. All right, to have an equation, should I work backwards? I'm trying to think. If I do x equals 4 as my solution, then I can do some things with that. I don't know. Listen, it can be an easy one. I can do something like 3 to the x equals 81 and solve from there. Or how about this? Let's make this our baseline equation. Let's do 3 to the x equals 81, but I want to do some things with it. If I subtract 5 from both sides, if I multiply both sides by 2, then I'll have 2 times 3 to the x power equals 162. And if I subtract 5 from both sides, I'll have, minus 5, and I'll have 157. All right, I'll make this my equation like that. So I'm doing some work based off something that I know where it'll say x equals 4, and then I go from there. I guess that makes most sense in how I can do that. So there's an equation with an exponential one where x equals 4, but there's the answer, I suppose. And then for part B, I need x equals -3 for a log equation. So for a log equation, let's think about that the other way. Now I need -3 to be my exponent. So let's make that be like 1 over, I already did 3 to a power. Let's do 5 to the power. So 1 over 125. If x is -3, sorry, I have an issue here. Then that means 5 to some power is 5 to the -3rd. So 5 to the x is 1 over 5 cubed, 1 over 125, right? What if I had, I just want to do a multiplication from this thing. Let's do 6. I'm going to do 625 here because that will clean up some of what I have. Wait, hold on. That's still an exponential equation. That's not logarithmic. What am I doing? What would it be a logarithmic equation that would have this? I can do, let's go back to log base 5 though. Log base 5 of, and I need -3 to be inside my x here. And let's say I want to get 25 inside of here. So I would need a 28, and this would have to be a 2. 5 squared, because 5 squared is 25. So I can do something like that. So this could be my x. I can do that. What if I multiply both sides by, say, -4? And I have -4 times the log base 5 of x plus 28 equals -8. And then we'll add 1 to both sides. -4 times log, I'm just being inventive. -4 times log of x plus 28. Hold on, what did I say I'd add? Just 1. Plus 1 equals -7. So I'll make this my equation as an official set. There's a logarithmic equation. That should be x equals -3. Because I need that to be -3 plus 28 to be 25. I need that to become 2, yada, yada. I think that's how that's going to work out there. So just testing the waters. Just playing with it. It's open-ended. I can play with it as I need to. It's kind of weird as far as me coming up with the problem with an answer in mind. I don't generally do it that way. But we got it. Like I said, you can have negative solutions. Number 66, thought-provoking. Give examples of logarithmic or exponential equations that have 1 solution, 2 solutions, and no solutions. Exponential might be the harder ones for me to think about. For both? So we have to come up with 6 things. So exponential, 1 solution is going to be easiest here. We can say 4 to the x power equals, 10. That's 1 solution. No solutions, we need to do something with more variable stuff on the other. No, we can do exponential. So let's do no solutions. I can say 4 to the x equals -1. That's not going to be possible. Now think about what you'd have to do here, right? You would be logging both sides, and we can't take the log of a negative. So that would be a no solutions one. 2 solutions, it would have to be some form of exponentials on both sides of the equation, or where you have maybe quadratics inside of your exponent set. So even if I had a 4 on this side, let's say to the x squared power, like now we're talking as far as solution things you can do. If I put 4 on this side here, we could say like 2x, and then boom, now you have 2 solutions because you set them equal to each other. X equals 0 and x equals 2 both work. It's a little weird though. I wonder if that's how we really want to say that, or if there's something else that we should be doing on that to make it more legit. We're probably not going to do equations with an exponential function and then a linear function, so I'd rather at least do something with a quadratic like that. I'm going to at least put here, let's put 2 to the x squared. I don't know. I'll just leave it like that. That's good. So those are 3 different answers. I kind of cheated on the quadratic there. That one's kind of harder to talk about without other kinds of problems we might not have seen. As far as logarithmic ones go, we can do something like log of x equals 47. Okay, there's only one answer that would go there. No solutions. Log of x equals something I don't know what I want to say, because you can get in an unlimited range. You want to make sure that your x's are extraneous in this case. Let's do something like log of x equals log of, well, this might sound like a little cheating, but like -3. Okay, hold on. That sounds like cheating. Let's do one where it doesn't look to be harmful, but then it becomes harmful, like 2x plus 3, like that. Because when we set them equal to each other, you subtract 2x from both, or you subtract 3 from both sides, subtract x from both sides, you get x equals -3, and then suddenly it doesn't work. So that one is extraneous. Maybe it's a little cheap, but it still works out that way. And a 2-solution one is where your quadratics both work in your scenario. Now, they set ones up with quadratics that work together. I don't want to make ones that kind of falter here, so let's just do a quadratic inside there. I'm going to kind of cheat again with this because I don't want to really come up with one on my own here. Log of x squared plus 9x, minus 8 equals, and then, let's do a different base. Log base 2 of this, and then let's even make it factorable. Plus 9x minus 8, I would have to subtract something over here. If I put a 2, 6 and 3. If I put a, I don't know, maybe it doesn't have a proper solution or set of rational solutions, but I think that would still have 2 solutions. It's still a quadratic you can solve. That would be 2 cubed, which is 8. Let's make this rational. Let's make this minus 10. 9, 12, 3. Hold on a second. Let's turn the 9 into a 6. 6x minus 10. Now that becomes x squared plus 6x minus 10 equals 8. Subtract 8 minus 16. 9 and -3. -9 and 3. Okay, so like that. Okay. Kind of cheating by putting the quadratic, but it still works. It was very thought-provoking. Really got it. Number 67 to 72, they say solve the equation. Fair enough. All right, these have different bases, so we're going to have to work off different bases to make some things happen. 2 to the x plus 3 power equals 5 to the 3x minus 1 power. Now, given that they are different bases, that doesn't mean you can't do some internal work to get things cooking, to get things started. So in this scenario here, we can log. Let's do a common log. I'm trying to decide if I want to do a common log or a log with a specific base in mind. Let's do a common log first, and if this works out just fine, I'll stick with that. So I'm going to log both sides like that. What it allows me to do is bring the x's out in front. X plus 3 times this log of 2 equals 3x minus 1 times this log of 5. I guess it's the same thing whether I did that or not. Now I distribute. Oh yeah, this next time I'll probably do with a single base, with a specific base like base 2 or base 5, but this first time we'll do it like this. What you want to do is get your x's on one side of the equation, but you must first distribute your x's into here. So I'll do x times log of 2 plus 3 times log of 2 equals 3x times log of 5 minus 1 times log of 5. So now I want to put my x's on one side of the equation here. Let's subtract. I'm going to subtract over here the x times log of 2, but I'm going to write it on this side. 3x times log of 5 minus x times log of 2 equals, then I add the log of 5 over here. I have 3 times log of 2 plus log of 5. You know, this is probably fine to do it this way. When I said write it as a specific log, actually I'm thinking not, because we got to calculate with this stuff anyway, and I think it would look trickier to have some fraction things. I can factor an x out of both terms. That's kind of my goal here. Get x's on one side of the equation to now factor x out of both terms right here. So this minus this equals this plus this. There kind of looks to be a pattern within here, none that I would identify immediately with, but the exact answer looks to be 3 times log of 2 plus log of 5. This is in expanded form, over 3 times log of 5 minus log of 2. So you can kind of see there's like a thing there. Nothing cancels. Nothing cancels in any sort of way. We work things out exactly as they are, and I can use the calculator to get that value. So we're going to do 3 times 3 times log of 2 plus log of 5 divided by 3 times log of 5 minus log of 2. .892, of course. 0.892. Of course that's the answer. I was totally guessing that would have been the answer. I mean, this is completely cool on that. Completely cool. All right, so that kind of works out there. I'm contemplating whether doing something with a specific base would be any better. Probably not. This is fine. See, even if I did a condensed form of this, the best thing I could do for myself would be maybe. So if I condense this, this would be log of 2 cubed over 5, so log of 8/5 divided by, and this is log of 5 cubed, or 125 over 2. That means that this would be log base 125 over 2 of 8/5. That's a condensed version of this answer. Or log base 62.5 of 1.6. And I don't think there's anything there that makes this even gentler. So I'd say what we were doing was fine. This is condensed form, like I said, and that's expanded form here. So I'm going to stick with that process if every question is like that. I'm going to stick with that. These are probably tougher questions as a whole, right? It's called critical thinking, literally. All right, number 68. Now there's 6 of these to do, so it's going to take a little bit of time. So number 68. Now in this case here, my hands might be tied when it comes to the whole log thingy, because log of 10 is 1. So let's see what happens in this case when you do log both sides, but something actually disappears. The difference is I still get to use log and don't have to change the base in my final calculation. So this time it's probably clean in a fine way. Log of this, log of this. Now log of 10 to that power is just that number, 3x minus 8. Meanwhile, the 5 minus x comes down and multiplies with the log of 2. Nothing's going to change as far as my goal. I still want to get x's on one side of the equation, but that doesn't happen unless I distribute this into these two terms here. So I get 3x minus 8 equals 5 times log of 2 plus x times log of 2. Now let's get our x terms on one side. I'll go ahead and subtract the x over. So I get 3x minus x times log of 2. I'm going to add the 8 over, equals 8 plus 5 times log of 2. Doesn't look like an exact inversion of things anymore this time. Factor an x out of these terms. I get 3 minus log of 2 equals, and I still have 8 plus 5 times log of 2. So now divide both sides by 3 times log of 2, and you get x equals 8 plus 5 times log of 2 over 3 minus log of 2. So let's calculate that one. I'll do it off screen. 8 plus 5 times log of 2 divided by 3 minus log. And I'm getting 3.522. 5217 something. So 3.522. Let me check on that one. Okay, I made a goof just because the number looks too different for my taste because of how these numbers panned out when you plug in 3. I was saying that might not be big enough or too small or what have you. That might not be small enough. So this one here, this was a minus, and this should still be a minus here, which means now this becomes a plus here. So that's my bad. Plus, plus, plus. So let's try that one again. So this would become plus there, and there we go. The number looks smaller now. If it was 5 minus 3 point something, 2 to the 1.5 power isn't going to come near 10 to the about 1.5 power. So this actually looks a little bit better here. It's not 3.522. We're looking at 2.879. At least now it looks smaller enough that I trust it. And I was trying to think what else looks wrong, and I think that's it. All right, my bad on that. Just poor distribution. Okay, number 69. Log base 3 of x minus 6 equals log base 9 of 2x. Now keep in mind, these are different bases. So we can't just set them equal to each other in that sort of way we did before. We're going to have to work some things out a little bit differently. And I'm kind of thinking about it. Maybe we can rewrite it like this. I don't know if this can be helpful or not, but log of x minus 6 over log of 3. Log of 2x over log of 9. I don't know if this helps or hurts or what. If you divide by log of 2x, then it's 2x to that power. Listen, there's more than one way to do this. I'm either between that or just raising these with a base of 3. The question is what happens here. 3 to the log base 9 of 2x. That's also a 3 squared. And I'm trying to think of what happens there. So I might have to ponder this one over as I'm working that out eventually. Let's first work through this and see what happens. Let's put x's on one side, but in a different way, right? Now it's log of x minus 6 over log of 2x equals log of 3 over log of 9. Actually, let's go the other way because I want to put log of 9 over log of 3. It at least will give me different numbers and I can play with those better. So let's do log of 2x over log of x minus 6 equals log of 9 over log of 3. If you think of these in terms of like converting to that log form, you can do log base x minus 6 of 2x equals log base 3 of 9. Now log base 3 of 9 is 2. That's why I wanted to go this way. Is 2. So this, okay, so this might work out. So log base x minus 6 of 2x equals 2. And now rewriting exponential form, that's x minus 6 squared equals 2x. Now I can at least solve that. I don't know if that's the best way to do the problem, but it's my go-to. I haven't done a problem like this before. X squared minus 12x plus 36 equals 2x. And we subtract 2x from both sides. And I don't see any factorization there. Maybe there is. I don't know. But this is x squared minus 14x. I'm going to complete the square. I get 49 equals negative 36 plus 49. Doesn't look like it has perfect squares. Probably didn't expect that. So x minus 7 quantity squared equals 13. Take the square root of both sides. You get x minus 7 equals plus or minus root 13. So x equals 7 plus or minus root 13. Now, as far as answers go, that can work because there's an x minus 6. 7 minus root 13 is going to be a no-go. So 7 plus root 13 should be fine. What is 7 plus root 13? It is 10.606 about. This is assuming that the minus thing is going to be extraneous. I'm just going to cross that out outright. There's my cross out for there. So 10.606 is what I'm going for number 69. An interesting bit. It seemed to work out based off a strategy. Once again, I need to ask myself when I think about it, what happens when you 3 to the log base 9 of something or log base 3 squared of something. And I'm not in the mindset to get that immediately. If I paused and looked at it, I'd be fine, but I don't want to waste your time with doing something wrong. So I'm going to stick with something right on these problems, and for now, this looks to be it. So number 70, we probably have to do more of the same, and I have to strategize on this one. Again, I haven't done these problems before. I've done problems like 67 and 68 before. Ones with logs of different bases, not really so much. So, and now 4 and 8. 4 and 8 are powers of 2. Maybe I can do something with that. Excuse me. I really do want to think of that. If I think of it as 2 squared and 2 cubed, does that help in the problem? If I say 2 squared to what power gives me x, 2 cubed what power gives me x, does that turn x into a square root? I'm not so sure. So I don't want to screw with that at all. Only these numbers aren't going to be clean no matter what we do. So unless I turn them into 2 squared and stuff, it's probably going to be a little iffy. If I do log of x over log of 4, I'm still going to try it this way. The difference is log of 8 over log of 4 is not clean. Equals log of 4x over log of 8. Let's divide the x, multiply the 8. So we'll have log of 4x over log of x equals, then we'll have log of 8 over log of 4. All right, I think I can still work off that a little bit. So this one is log base x of 4x. Now as side work here, remember this becomes log base 4 of 8, and I'm trying to ask myself 4 to what power is 8, so I can still match this up, which means I could have done something here before. I don't know what specifically. Again, I'm still having trouble with that. So that's 3 over 2. So log base x of 4x is 3 over 2. So when rewritten in exponential form, that's x to the 3/2 power equals 4x. If I square both sides, I'll have x cubed equals 16x squared. I have to be mindful of solutions that wouldn't work. I can't take square roots of negatives. So x here has to be greater than or equal to 0. That would have been true from the beginning, actually. So I guess that's fine. X has to be greater than 0 anyway. So I guess that doesn't matter. And I can subtract 16x squared over. I can factor in x squared out. And x either equals 0, which is not allowed for our case here, or x equals 16. Does that work? Log base 4 of 16 is 2. Log base 8 of 64 is 2. That does work. There must be easier versions of that I'm not seeing. And I don't know what to see with them. But doing what I did there, it did work. So I'm not going to refrain from what's working. Okay, number 71. I have 2 to the 2x minus 12 times 2 to the x plus 32 equals 0. I apologize if any of these things take a while to do. This one, I see something different that I know how to do. Now, this 2 to the 2x can be rewritten as, and I'm going to actually put the parentheses around the 2 to the x to emphasize more what I'm looking at. This is 2 to the x squared. The reason I bring this up is this is like that u substitution quadratic form business. This 2 to the x can be like a u. This is like u squared minus 12u plus 32 equals 0. So we can factor this out into u minus 8 times u minus 4, which means this is 2 to the x minus 8 times 2 to the x minus 4. So that's my u substitution version of that. First I looked at the problem, I'm like, what are you doing? Now I realize what this thing is. So either 2 to the x minus 8 equals 0 or 2 to the x minus 4 equals 0. So 2 to the x equals 8, in which case x would have to equal 3, or 2 to the x equals 4, in which case x would have to equal 2. Not a plus or minus. We're not doing square roots. If you're doing any form of log stuff, this is what you'd get as well. Now, do either of those work? Sure. These are exponential functions. It's not logarithmic. We're all good for that one. So x equals 3, x equals 2. I'm good with them. Number 72, maybe more of the same kind of question, which is good. The two questions before were making me a little nervous in terms of was I doing them right or wrong. I know the 16 was right because I plugged it in and it actually worked out, so I felt pretty good about that one. 5 to the 2x plus 20 times 5 to the x minus 125 equals 0. Yeah, this is more of the same here. Now this is 5 to the x squared. So remember, treat that like a u, if you will, as its own variable. And let's see if this is factorable. So this factors into 5 to the x plus 25 and 5 to the x minus 5. So this is 25 times negative 5 is this, 25 minus 5 is that. So 5 to the x equals plus 25 equals 0. 5 to the x equals negative 25. That's not possible. So you'll have to leave that as is. You can't do anything with that. You can't raise a positive power to an exponent and get a negative number. 5 to the x minus 5 equals 0. That's 5 to the x equals positive 5. Positive 5, therefore x is 1. X equals 1 in that scenario. And 1 is fine for an exponential equation such as that one. So as far as critical thinking, I have critically thought, and I'm good. All right, number 73. I have two more questions. 73. In exercises 67 to 70, you solved exponential logarithmic equations with different bases. Describe general methods for solving such equations. My thing that I did, and I don't know if this was proper, but I had to get my x's on one side of the equation. So my general focus was to get x's on one side of the equation and eventually out of their exponents / logarithms. So for me to do this, like on 67 and 68, you'll see a common practice here. Not a common practice, but you'll see that, where did it start? 67? On 67 and 68, you'll see that I did an immediate logging of both sides here. Boom, boom, to ground the x's out of the exponents. And then my goal is to get x's on one side of the equation as terms. So that came right here. I got 3x times this minus x times that, which made it a common factor, and that got me where I was. I did the same thing here. I did one quick screw up where this minus x turned into a plus x. I recognized it and fixed it, so we're all good there. That's that one. This one was a little different, and I'm sure I did more work than I needed to. I'm sure there's a faster approach. If I do 3 raised to these powers, there's probably a good way to state how log base 9 of that works, and it's probably right in front of my face. You probably got to take half of the 2x and turn it into x something. There's something there, I'm sure. I just didn't want to spend time doing it and being wrong. But here, when I have both sides log there, I rewrote the bases as here, but I got x's on one side of the equation, so I could rewrite it as a single log to eventually get rid of the log. And that's what I did also with this problem as well. Got the x's on one side of the equation, so I could rewrite it as a single log and eventually get rid of the log. Treat it into that other form and work some things out. So that was my general thing. I don't know if that's the best answer for it, but I don't think I faltered. I believe those are correct. So that's my general method there. I know there's more to state, but that's the general thing. Number 74, last question. When x-rays, how long have we gone? Oh, yeesh. Getting near 3 hours. When x-rays of a fixed wavelength strike a material x centimeters thick, the intensity I of x of the x-rays, whoa, look at this equation, transmitted through the material is given by I of x equals, this got me standing up. This got my thing. First of all, there's a subscript, there's the E, and there's mu. Where I naught is the initial intensity, mu is a value that depends on the type of material that's in the table, the type of material, and the wavelength of the x-rays. The table shows the values of mu for various materials and x-rays of medium wavelength. So we have, there we go, wasn't pasting, aluminum, copper, and the lead. Getting the lead out. Find the thickness of aluminum shielding that reduces the intensity of x-rays to 30% of their initial intensity. Hint, find the value for which I of x equals 0.3 times I naught. I figured you would have divided I sub x by I naught and gotten 0.3. Oh, yeah, that is what you're doing. That's what that shows. Yeah, I would have done the same thing. Remember, there was the question on doubling. It's whatever this was. If this is 200, then this is 100. Well, if this is 100, 30% of that is 30, and 100 divided by 30 is 0.3. So no matter what on these ones, I'm setting 0.3 equal to, and I'm getting e to all these different things. So aluminum shielding, aluminum's 0.43. So negative mu to the x power. That's our setup. I'm going to natural log both sides like that. And I have natural log of 0.3 equals negative 0.43 times x. So x equals natural log of 0.3 over negative 0.43. Negative 0.43. And this answer is 2.7999, so around 2.89999. X is around 2.8 thickness. What's this? Centimeters? Centimeters of thickness. That's for aluminum. These part B and part C are pretty fast. Repeat for copper and lead. So if they're just taking this number and doing negative down here below, I can do X for this one is natural log of, again, 0.3 over negative 3.2. And for the next one, over negative 43. So part C, X is natural log of 0.3 over negative 43. Once again, if there's a pattern, you learn off that pattern and you do that. So I'm going to do those in the calculator as well. They obviously become less thick as lead is needs less thickness for the shielding. So let's do over, oh wait, negative 43. Oh, 0.43 and 43. So what, 100 times less? We'll see what that is eventually. But negative 3.2 is 0.376. I'll put 0.38 centimeters. And then, so I'll put 0.80 because it was 2.7999. And then this one, I guess it's going to be 0.028 for this one because it's 100 times, what's that, 43? You're dividing by something 100 times more. So yeah, 0.028. So should I go to 3? Should I go to 3 decimal places then? Let's go to 3 decimal places just because how particular this thing's going to get. So this was 0.800. That's totally crazy. But this is a 6. And then there's that one there. Okay, part D. Your dentist puts a lead apron on before taking x-rays of your teeth to protect you from harmful radiation. Based on your results from parts A to C, explain why lead is a better material to use than aluminum copper. Lead has more, let's see, what do they call it? Shielding. X-rays of fire length thick. The intensity transmitted through the thing. I don't see initial intensity. Depends on the tail. Shows the various materials. It requires less thickness. Lead requires less thickness to shield, to reduce shielding. X-ray shielding? Let's see, what do they call it? That's what I'm trying to figure out. The intensity of X-rays. Hold on, where did they say the word shield? I want to find where they said that because that seemed, oh, aluminum shielding, I see. So lead shielding requires less thickness to reduce the intensity of X-rays overall. So less material is required. Basically, if all costs were the same, if all things were alike, you need less of this than you need versus the other things because you need literally 100 times less than aluminum. 100 times less than aluminum. And that's what I was kind of saying with those numbers. Aluminum. I was going to say aluminium. Which is, of course, the Brit way of speaking it. And speaking of which, that'll do it for this one. That doesn't sound British. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Quite an undertaking on some of the problems there, but I think we achieved them all. Apologies if I had a little screw up and said, whoops, got to fix that one, but I think we got there. Thank you so much. Take care. I'm going to see you in the next one.